So as the title says, this is BGP multi-homing techniques tutorial. So what this does, this really builds on the tutorial I did at the last NANOG, which was really introductory BGP techniques for service providers. So it just did a fairly high-level introduction to BGP, the attributes, how you go about configuring it, what the best practices in the industry pretty much are, what to configure, what not to configure, and so forth. So this follows on from that, and it starts down the path of multi-homing. When I was first asked to do these, it was like, okay, can you do a tutorial on multi-homing, please? And multi-homing is such a vast subject, and it's also it's very dependent on your local topology, how you connect to your different providers, who your providers are, where they are, in other words, which geography, and so forth. So I've tried to do a fairly generic wander through the middle of the fundamentals of multi-homing, so what you really need to do as the basics to get you started. And I think once you've figured out the basics to the level I've gone in this tutorial, pretty much any scenario will actually work for you. At least that's what I've found as I've tried to develop this content over the last few years. My name is Philip Smith, work for Cisco, also on the NANOG steering committee, which is why I've got a blue badge here in case you're wondering why I've got a different color from you. And you'll probably see some other members of the steering committee and program committee wandering around, and they all have either blue badges or green badges. And I think you'll see Steve Feldman, who did come in here and said, "Ooh, it's Philip." He's got a yellow badge, which is does he have a yellow badge or does he have a green badge? Don't remember. Anyway, so this is really the main thing, the main issues, differences. So let's make a start to this. I'm not sure if I'm going to get through all the content in the 3 hours that I've got. The first half of the presentation is really going over some of the basics. The second half I go into some bit more detailed load balancing. Presentation slides, as I said before we started properly, are up there. They also should be on the NANOG website. Well, on the ftpeng.cisco.com site is the latest, because I've made a couple of changes over what I submitted to the NANOG folks a couple of days ago. So this session is being recorded, so if you want to ask any questions, please use the microphone so that the people who watch this recording later on actually can hear your question. So the microphone's in the middle, so please use that if you have any questions. As I say, feel free to ask questions anytime. I mean, you can interrupt the flow, you don't have to wait to the break or anything like that. Quite happy to have this as an interactive session if you want to make it that. I mean, if you're quite happy just listening to me chattering away here, that's fine too. I've got a load of configuration examples in this. They're all using Cisco iOS CLI as opposed to anything else. I mean, if you came to the V6 routing tutorial this morning, you saw that I had 3 CLIs up there. As you see, iOS is fairly compact. If we go down the path of Junos or iOS XR, it's going to start multiplying the slides up big time. So I've tried to keep this as compact as possible. The idea behind the configuration examples is that you can take these away, try them out on your own network, in your own lab, on your own routers, and get some idea of what's actually by and large have been taken from real live routers, so they're not made up. Okay, they've come from real life routers, mostly from stuff that I used before I worked for Cisco. So it's from the ISP I used to work for before I was at Cisco. We had loads and loads of configuration templates, and basically what you see in the CLI examples here are modifications of those templates. Presentation is aimed at service providers by and large, but a lot of the techniques will work for many enterprises now. I mean, the difference between how an enterprise runs its large network and how a service provider runs the network is kind of blurring, merging these days. So a lot of the techniques will actually work for enterprises also. So what I'm going to cover are basically all these. Why we go about multi-homing, going through some of the definitions, some of the options available, how we go about preparing the network. So if you're running no BGP at all, you can actually get ready by running BGP within your backbone to then head off and do some multi-homing. Then we'll go through some basic multi-homing, so it's just doing enough to get inbound load balancing. Then the service provider multi-homing is a bit more complex, trying to get load balancing for outbound traffic as well. And then we'll finish off by just showing you some examples of how ISPs are using communities for the multi-homing needs as well. So hopefully I can cram that all into the time that I've got. So why do we head off multi-homing? Why do we do it? Well, the main issue is this, redundancy. 10 years ago, 15 years ago, the internet was, depending where you were in the world, was pretty much a toy. When I started off in Europe with the UK's first ISP, it was very, very difficult to try and convince any business to abandon their happy X25 or frame relay networks to transfer whatever they need to transfer to this wonderful new, untested, as far as they were concerned, IP thing. Of course, these days the internet is pretty much what everybody uses for business to business communication. You know, we as the service providers sitting underneath are really there in the business of passing packets that our customers want to send, and that's all we do. And it's a lot of these organizations that you have, they want to multi-home. You as a service provider wants to multi-home. You want redundancy in your network. If you're dependent on, say, just a single router for your external connectivity, what happens when that router breaks? What happens when there's a configuration error on that router? Or what happens when there's a software problem? Could be a software feature, bug, or something like that causes it to cease functioning. Well, your network is completely dependent on that one router. That router's out of the equation, you have no more network connectivity. Now, when the internet was a toy, that probably didn't matter so much. You just go, well, fix it, and then we'll carry on working. These days, if your business is certainly involved in millions of dollars a day, a week, a month, a year, it becomes a very, very serious issue because it basically means lost revenue. So you do not want to depend on any single device in your network. If you look in the design of any major service provider backbone these days, you find that there's almost pretty much two of everything everywhere. There's redundancy, right? So one router breaks, you get redundancy from one sitting in parallel. So that's probably the first reason, local router. So you find that many organizations who multi-home are using two routers to do that. One router breaks, they still get backup with the other one. The WAN media, that can be the next issue. Okay, your link going from you to your upstream service provider, if that link breaks, well, you're cut off. So what you tend to do is you get a second WAN connection. Now it could be second fiber, it could be backed up with microwave, it could be backed up with wireless, anything like that. Okay? Here you work around physical failure, so somebody comes along with an excavator, breaks a cable, digs it all up, something like that. Or somewhere in the transmission system breaks, it could be the carrier decide to do major maintenance, and, well, they basically break all your connections. So if you only had one connection to your upstream, well, you're kind of bust there as well. And by redundant media, I mean, some ISPs take this really seriously. Redundant media quite often means it is redundant all the way from their premises to their upstream service provider's premises. So they work with their providers to make sure that the fiber path is completely diverse all the way along the way. I mean, you don't want to end up with something like we had way back in the early 90s. Sitting there in the UK, we go to British Telecom, we go to Cable and Wireless and say, hey guys, please provide us with redundant connectivity between here and Washington. And it was like, yeah, no problem. And we found out that the two circuits that they were giving us, the 264K links actually ran on the same transatlantic cable. Now, the chances of transatlantic cable breaking are pretty low, but pretty low is not zero. And when they did break, of course, we lost both our connections. So thereafter, it was basically we had the two telco providers sit in the same room and say, right, you're going to guarantee us a fiber path from Cambridge and London all the way to Washington and New York that's going to be completely diverse all the way. Okay? And you find, bringing it into modern times, that many ISPs work like that as well. I've started mentioning the Taiwanese earthquake in the context of these presentations. I mean, anybody who was burnt by that knew that one as well. Yeah, there were eight cables going basically from Southeast Asia to, well, variably Japan and across the Pacific to the US and Canada. But the problem is, these 8 cables all ran between Taiwan and the Philippines. There's a narrow strait between the Taiwan and the Philippines, and all these 8 cables ran within about 100 miles of each other, not even that much, probably 60 miles of each other. And there was this massive earthquake, 26th of December last year, that, well, basically caused a massive landslip under the sea that broke, I think it was 8 of the 9 cables that went through that particular path. So the ISPs who thought they had even fiber redundancy there didn't, because the cables went in pretty close proximity to each other. So the proper redundancy now that's been considered, certainly for Southeast Asia and South Asia, pretty much anywhere from Thailand, even Hong Kong, heading west, they're looking quite seriously at going past India, through the Gulf regions, through the Mediterranean into Europe as the alternative path. Because at least, if one side of the globe breaks, the other side will carry on. It's that serious level that they're actually looking at it. It's going to cost them more, but at least they can be guaranteed that if one bit disappears, they get the backup. So this is a major reason to multi-home. Now, 10 years ago, this would have been no big deal, but because the internet is such a big deal in many parts of the world now, that people are seriously looking at redundancy and therefore multi-homing. And the third point there is the upstream service provider. Your upstream service provider, do they run a more perfect network than you do? Well, if they did, then you could rely completely on them. But it's actually quite unusual for you to just say, oh yeah, my upstream is perfect. I mean, that never really happens. They could do maintenance. They could break the router, whatever. They could do an upgrade that doesn't work. Or they could have a hardware problem they can't do anything about. So that could be the other issue there. This was always a fun thing when, in our early days, we were sitting there, UUNet in Europe, and, well, there's UUNet in the US, so they did the maintenance. Well, when do you think? They did it 4 a.m. to 7 a.m. East Coast time, which wasn't actually too helpful in Europe because that tended to be midday and peak internet traffic. So we weren't that impressed when the guys in Washington decided that, yeah, we're going to do our major network maintenance 4 a.m. to 7 a.m. on our transatlantic connection, and the POP that handled that, which had brought us out completely. So upstream service provider, even the regular maintenance stuff could completely blow your network connectivity away. So you find that ISPs have a requirement to connect to more than one upstream. Okay, so that becomes a fairly major thing. You don't want it to be dependent on one upstream service provider. Reliability, well, this kind of follows on from redundancy. I mean, if you don't have your redundancy in your network, you ain't got any reliability. You're running business critical applications. I mean, we are always told inside Cisco how important the CCO portal is. I mean, there's pretty much all the Cisco resellers and so forth do their business through the CCO portal. All the orders that are made go through that. So if that doesn't work for any length of time, people can't put their orders in, etc., etc. So it's highly important that that website, in other words, that business portal of ours, is available all the time. So we are actually heavily multiply redundant. We have that continuous availability. If you've got no redundancy, you don't have reliability, and therefore you get the loss of revenue. A lot of ISPs these days, I mean, a lot of ISPs the marketing people say, oh yeah, we guarantee 100% availability and so forth. If you're actually going to provide that availability guarantee, you need something in the network that's actually going to back this up. I mean, you can't just say, oh yeah, we're going to do it and not meet it. I mean, some people give the 100% availability, then say, okay, for every minute you don't get connectivity, we'll refund you the cost of that minute. So when it comes down to it, you actually find you're not being refunded that much at all. I mean, some ISPs were bolder, like we were in the UK back in the early 90s. I mean, we actually said 99.5% availability. We refund you a month if we don't meet that availability in a month. And that did hurt. I mean, that could hurt. Seriously, because it's a month of revenue at that time. We would refund if the network wasn't available, which was a big boast that nobody even could match. And Think about it, 1994 with the old routers and the lack of features you had in those days to actually meet that availability. And we easily met it. It was like 99.8, 99.75 we met most of the time. But that's the sort of thing you give people a sense of reliability of the network. You need to be able to back that one up. Supply diversity. This is more common these days. Many businesses demand supply diversity as a matter of course. You don't want to be tied into one supplier. So it's an internet connection from 2 or more suppliers. You see more ISPs getting equipment from 2 or more vendors. Simply they don't want to be stuck with one vendor who could maybe let them down at some stage and then affect their business. So you find 2 of everything is really common. In some parts of the world, I still pity the ISPs who do major RFPs that say, design me a network. And they send this out to all the different vendors, and then they just select one vendor as the final thing, and I go, what's the point of even trying to do this? You're basically not giving yourself the ability to run a reliable or even a profitable business because you've tied yourself into a particular design rather than doing something that you want to do. So you look at the supplier situation, you've got 2 or more diverse WAN paths. I mean, when we started off in the UK in '92, we started off with 2 suppliers. So British Telecom and Cable and Wireless were providing connectivity for us, both within our backbone in the UK and then more later on into Europe and across the Atlantic as well. And we used different undersea cables and so forth. And then as the telecoms deregulated in Europe, then the competing cable companies, the electricity companies, they all started providing connectivity services as well. And that we used all those, got more suppliers for the connections, and it gave us better reliability for the network. 2 or more exit points. I mean, anybody who's designed data centers will know what the 2 or more exit points mean. Generally in a data center, you see the fiber go out opposite corners of the building. There's a reason for that. And if fiber went out the same side of the building and somebody decided, hey, I'm going to build a new building next door, and they get their old excavator, caterpillar out and dig some deep holes and cut through all your fiber, you cut off the data center. So you tend to find that they have them going out opposite corners. Even if somebody dug a trench 90% of the way around, the chances are you still have one connection working. 2 or more international connections. I mean, that's pretty common for many providers around the world. It's generally 2 of everything. You look inside backbone networks, you find 2 routers, 2 core routers. I use 2 border routers. You have, look in your name servers, 2 DNS servers. It's 2 of pretty much everything is used. And it's sort of the usual thing I say in any of these presentations. Okay, how many people flew here? So did you look out the window and count how many engines are on the plane? Well, it's got at least 2, doesn't it? There is a reason for this. The other reason, well, it's not really a reason for multi-homing, is leverage. And there you want to play one ISP off against the other, or play one supplier off against the other. I'm not recommending this, but in reality it happens an awful lot. If you get connection from just one upstream, well, they can charge what they like. Okay, because they're not having to compete against anybody. But if you get a connection from 2 upstreams, then you compare them all the time. So you can use what the quality of service that one upstream gives you to beat up the other one. I see this more in the developing parts of the internet, where the ISP in the country gets 1 satellite connection, and he's like, oh man, this is really, really expensive and so forth. And I go to him and say, well, get a 2nd connection. But that's going to cost me even more. Just try it. Just do some research. Go and see. And what they find is they usually can get 2 connections of equal bandwidth for the same price they're paying for the 1 connection. Because the supplier of the 1 connection knows they have a completely captive customer, whereas as soon as they get involved, go finding out from another one, the upstream goes, well, we can do you a special price. So 50% comes off, for example. So they immediately can make that saving. And having been through so many ISPs going through this particular path, they've multi-homed, but they've multi-homed to reduce the price that they pay per megabyte. So a service quality, it's the price of the service as well, service offerings. Some ISPs say, yeah, we'll give you 8 megabit connection. And then the question is, well, is it really an 8 megabit connection, or is the circuit clocked at 8 megabits per second? There is a difference. A lot of the newcomers don't realize that there actually is a difference. Many of the backbone providers oversubscribe the networks. Now, how much do they oversubscribe? Is it 1 times, 2 times, 5 times, 10 times? Well, the different providers oversubscribe at different amounts. And very much in the transit business, you do tend to get what you pay for. So you may get an 8 megabit connection from somebody who's 10 times oversubscribed, and an 8 megabit connection from somebody who's 2 times oversubscribed. And you'll be amazed at the performance difference. So they can use that kind of thing really for playing the ISPs with their service quality and their service offerings. And of course, availability as well. And suddenly when it gets into transoceanic cables and using satellite access or even wireless access, availability does matter. Different satellites have different reliabilities. They could be fading out, in and out, and so forth. Or something with the VSATs, weather can make a big difference at times. Wireless, well, with any of the 802.11 wireless access families, then you can have endless entertainment. Somebody puts up the same channel or overlapping channel on the mast that you're using, and boom, your connection suddenly disappears. All that kind of stuff. So I've talked at the high level. It's very, very easy to demand it. I mean, this is the sort of thing your CEO can come in or your CTO can come in and say, yep, we need to do this because it's good. And so that means you've got to go onto your router and type in the CTO says it's good command that magically gives you multi-homing, which of course doesn't exist. Right, so you're left as the poor network engineer to try and make all this work. So you've got to do the dance with the registries and your upstream ISPs and so forth to try and deliver what your CTO or CEO has pretty much demanded in a 5-minute meeting with them. Okay, so what do we do? Well, before we head into that, let's look at some basics first. So some of the definitions. What is multi-homing? Well, my definition is, and people seem to spend years trying to define what multi-homing is. Mine is this: more than one link external to the local network. So whether it's 2 more links to the same ISP or 2 more links to different ISPs. I mean, that's good enough. That is multi-homing. If you've got 2 circuits to the same upstream, you are multi-homed to that upstream. Usually you have 2 external facing routers. If you have 1 external facing router, you run into the redundancy problem. If you have 1 router, it dies, you're dead. So if you want proper redundancy, you want to justify spending all this money for multi-homing, get 2 routers. Okay? It's generally pretty easy to get a second router into the equation. I'm always disappointed when I see people that have sat through the tutorial and say, yeah, we followed your advice about 2, but our vendor tells us their router's 100% reliable. Rubbish. Okay? Doesn't happen. No matter what they say, they'll sell you dual processors and super duper high availability software. Doesn't happen. Get 2 routers. No. Doesn't happen. Okay? So it's better getting 2 routers, put them side by side, or separate power, all the usual good design stuff, separate connections, and that is really the only sensible way forward. With a single router, you've got link and provider redundancy only, but you don't have the router redundancy that you also need. You also need an AS number, because you're going to run BGP. AS number is a 16-bit integer at the moment. Well, it's actually a 32-bit integer, but current practice at the moment on the operations side is 16-bit integer. First 64,000 are available for use on the public internet. The remaining 1,023 are for private use only. ASNs are now extended to 32 bits, so RFC 4893 describes all that. The notation is still going through a little bit of discussion. I mean, some people want 32-bit notation, so you just have numbers 0 up to 4 billion. Other people want the 16.16 notation. If you're on the tutorial this morning, the routing tutorial, you saw one of the routers I was using 32-bit AS number in the dot notation. I find the dot notation easier to look at, but then there are issues with the dot notation as well, especially when it comes to handling regular expressions. I'm not going to wander into any of that at the moment, but that's just one of the issues. Actually, this is now unexpired. I should fix this. This has gone up to, I'll fix it. Sorry, I should have updated this internet draft. I think George has wound it up to version 4 now. Okay, so it's internet draft just by George Michelson, which describes this. So that's pretty much where it's got at this stage. The other thing to note is AS23456 is being used to 32-bit ASNs. So once you wander into using BGP and have a look at what you see in the BGP table, you see more and more of AS23456 appearing. And that's basically your window into the 32-bit ASN world. Okay, so any 32-bit AS number in your world is represented as AS23456. And there's a bit of magic that makes all this work properly. So ASNs come from the regional internet registries. So if you're a member of the registry at the moment, you'll get an ASN as part of your membership. So you already get v4 address space from the registry. You can also get AS numbers. And of course, as we were talking this morning, you get v6 addresses as well. Current 16-bit allocations have been made up to 45,000 to the registries from the IANA. And you see about 26,500 of those on the public internet. At least my view of the public internet shows that. The registries have also received 1,024-bit, 1,024 32-bit ASNs, and there are about 5 of these visible on the internet. I think there were 6 the last time I looked, visible on the internet. So these are early adopters who are playing with 32-bit AS numbers. Just a note about private ASs. They're used for ISPs with customers multi-homed onto their backbone. So RFC 2270 describes that. I'm going to go through one scenario that describes how the RFC 2270 multi-homing is actually done, just so you see how it works. You also find that private ASNs are used quite a bit with corporate networks. They may have head office using the public AS number where they multi-home, and then all the regional offices are put into their own autonomous system. So at least the managers of the regional offices, the network managers, can run their own small network there and talk BGP to the head office, rather than trying to run an interior routing protocol all the way around the world. That's my favorite way of trying to do this. The other place you see private ASNs used are within BGP confederations, which is an old BGP scaling technique, which I'm not going to talk about either. One best practice thing, private ASNs must be removed from all prefixes announced to the public internet. So in your BGP template, just add this as one of the configuration lines. So neighbor in iOS, neighbor, whatever, remove private AS. And that will strip out any private ASs that you're using within your backbone or for your customers who multi-home onto your backbone. Okay, so like private addresses, private ASN should not be leaked out to the internet. I mean, I was just looking before I started the presentation. There's one thing that I do, and I posted the NANOG list for those of you who don't filter it out, is this weekly routing table report, which kind of looks at the BGP table and per registry region and just shows the size and what's happening and so forth. And I was looking at today's run of the results, and I see that one ISP is announcing a huge number of private ASNs. So that's popped up. So, you know, if you announce a private ASN, I will see you, and I will publish it on a lot of the mailing lists. I send this report to most of the mailing lists, so it does become pretty visible that you're doing this. People aren't generally too bad, but you do see them appear from time to time. Okay, the question for the benefit of the video was, don't most companies turn off your link if they see that happening? Some companies do, but a lot of companies are quite happy to receive your money. So a lot of companies, because they're happy to receive your money, they don't care what they do. I wish they would stop doing the announcements, but no, it depends which part of the world you're in, and you tend to find that the more developed parts of the internet, the more established parts of the internet, the ISPs there, the operators do pay good attention to good practice. And you find in the newer parts of the internet, it's show us your money. We'll take your money. We'll write address space that is not yours. We'll write any old rubbish you want us to write. And that's quite common. I mean, there's some amazing, I mean, if you sit on enough of the NOG list, you'll see some incredible mistakes that they made. You know, like there's one ISP in China announcing a huge chunk of address space that simply wasn't theirs. And it was visible in the global table. And nobody cared. Because it was an aggregate covering sub-prefixes that were already being announced by the ISPs who owned or used that address space. And nobody cared. I mean, their upstreams, which were actually based here, didn't care either, which makes me wonder. So yeah, I mean, you'd hope. I mean, certainly an ISP I would be running if I was still running one. I mean, we did all this at UUNet back in those days. We just, what a customer was entitled to announce is what they got to announce. And if they came along with more address space or another AS number, they had to tell us. And they had to prove that it was actually their stuff as well. They couldn't just say, oh, please write this. Hey, we'll pay you an extra $20 a month or something. Okay, where there's a lot of people that are not that scrupulous. It's part of the thing. If you're in the job that I'm doing, you get to see an awful lot of BGP configurations, and you'd be terrified if you saw the amount of BGP configurations that are accept everything in and spew everything out. There are so many people doing that, and it's frightening. It's amazing the internet works at all, quite frankly. Okay, let's not go down that path, but I talk about this enough in the best practices presentation, so this is multi-homing. Let's try and stay here. Right, configuring policy. I'm just going to use the 3 basic principles for IIS configuration examples. I'm going to keep this simple, because I'm trying to teach multi-homing, not how to be a guru. Yes, I get asked to do advanced multi-homing presentations, but I can't really do that from my side, because as soon as you get into advanced stuff, you end up doing very, very specific configurations for very specific situations. And given the 26,000 autonomous systems visible in the BGP table, it means to me that there must be around about 26,000 service providers. So I think one of the 26,000 could come up here and just do a presentation on advanced BGP. Please. The NANOG folks would really love you to do that. Anyway, apart from that marketing, I'm going to keep all this stuff nice and simple. So we're going to use prefix lists in iOS to filter prefixes, filter lists to filter AS numbers, or based on AS paths, and we're going to use route maps to apply policy. Yes, we can use route maps to do the above 2 things as well, but that starts getting complicated, and well, if you don't know how the simple stuff works, it's not much point trying to teach the advanced as well. Policy tools, if you don't remember these, suggestion, have a look at the NANOG 40 BGP techniques presentation. And if you go to the same FTP site I showed up there, you'll see NANOG 40 BGP techniques. Or go to the last NANOG website for NANOG 40 and grab the presentation there. Because there I've covered what the different BGP attributes are. So local preference, which lets you manipulate outbound traffic flows from your network. You set local preference on inbound routing announcements. MED, you set MEDs on outbound routing announcements, lets you manipulate inbound traffic flows, but it only works in your AS. Okay? It's only for local scope. MEDs are not passed on between autonomous systems. If you want to do this type of inbound traffic flow manipulation between different autonomous systems, you're going to have to use the AS path prepend. That is the only weapon that you really have. Okay? And the final one is communities. Communities cover quite a lot of all this and a bit more. When we get right to the end of this, in the second half, you'll see how ISPs are using BGP communities for applying BGP policy as well. I haven't put a huge number of examples because, again, they get really complex and they depend very much on the different service providers. But I've given you some ideas just to show you what can be done. So those are the policy tools we have. There is nothing else. Okay? Quite seriously, there is nothing else. If you can handle these 4 BGP attributes and know how to manipulate them properly, you can do any and all types of multi-homing, traffic engineering, etc. That you'll ever need. Right? There isn't anything else. So really, multi-homing is all about getting to the grips of configuring those 4 attributes on your router. Now, some of the assumptions. Again, this doesn't seem to be current practice, and I'm completely bewildered why. Okay, the first assumption, must announce assigned address block to the internet. So you go to your registry, you get your /21. The expectation from the registry is that you actually announce this /21. You do not get, what is it, 8 or 16 or 32 or 64 Class Cs anymore. I'm amazed how many emails I still get saying, hey Philip, I've got 32 Class Cs from APNIC. APNIC did not ever hand out Class Cs. In fact, Class Cs disappeared about the time APNIC was born in 1994. you got an address block. You probably got a 19 if you got 32 class seats. Okay? You get a /19. The expectation is, if you have been to the LIR training that APNIC offers, is that you announce this /19. Okay? Current registry minimum allocation is a /21. The expectation is you announce the address block that you get. You can also announce sub-prefixes of this address block. The sub-prefixes you announce, reachability of those may not be guaranteed. There's some ISPs who actually filter on the registry boundaries. Right, the registries, as I'll show in the next slide, they publish the minimum allocations per address block. And some of these ISPs will filter exactly on that allocation boundary. So if you announce lots of /24s and the minimum allocation was a 21, you have no connectivity to the ISPs who are doing that filtering. Is it their problem? No, it is your problem. Keep announcing the aggregate. Okay, it's really important to do that. So several ISPs will filter the registry blocks on this boundary, or whatever the boundary is for the particular block. Several ISPs will filter the rest of address space according to the IANA assignments. Okay, so if IANA has said this /8 is not in use, the ISP will put in a BGP filter that says block this /8 or whatever. I was in the ISP who emailed me yesterday. I was in the flight here from San Francisco. Hey, Philip, can you let me know what you think of this BGP configuration? And he'd obviously grabbed a BGP configuration that had been in use probably, I don't know, about 4 years ago. And if you remember what the IANA reserved address space was 4 years ago, and if you know what it is now, IANA has handed out 1 or 2 /8s in the last 4 years. I think it's about 30, 35, almost, yeah, about 35 they've handed out in the last 4 years. So they basically, I said to him, okay, you've cut yourself off from 35 /8s worth of the internet. So I haven't got a reply yet. So it's really, if you're going to start doing filtering of the rest of address space, be very, very careful. You need to keep it up to date. So this activity is called net police by some people. I mean, there's no such thing as net police, but some ISPs, all taking after Sean Duran when he was at Sprint, again in the mid-90s, Sean did very serious filtering of routable and non-routable address space, so other ISPs actually copied this as well. And so at the time, this was all called net police. There are no net police as such. There's nobody going to come along in the patrol car and say, "Ooh, you shouldn't be doing this, have to arrest you." I wish there were in some cases, but anyway. Now, so the registries publish the minimum sizes per /8 block that they got. So these are the current URLs. You can go there and find what the minimum allocation is for each /8. That's up to date. I mean, I looked at those a few days ago, and they all do list what the minimum allocations for each block are. IANA publishes the address space that is assigned to end sites and allocated to the registry, so that's there, so they keep that up to date. Now that Leo Vigoda is working for IANA, he's working pretty hard at making all that data really good data, so you can actually trust what the IANA database has, which is nice. So several ISPs will actually use this information to help with their filters. Now, the whole big deal about the net police thing is this. A lot of ISPs seem to want to do the net police thing, and I can understand why. There are one or two issues, and it affects more the developing parts of the internet than the established parts. The idea is it's meant to punish ISPs who pollute the routing table with specifics rather than announcing aggregates. So the routing table today, 234,000 prefixes in my view. If you actually sit down and try and aggregate all this, I mean, I do that in the software that I run, but if you actually aggregate this, you can pull the internet itself down to about 130,000 prefixes. So there's about 100,000 prefixes there of plain junk. Okay, that's simply, if you threw it all away, you wouldn't lose any connectivity whatsoever, which I think is quite incredible. And I mean, it's back to the observation, well, don't ISPs do anything about it? The answer is no. Nobody's doing anything about it. Or as Randy has always said, I encourage my competitors to do nothing. I mean, if you're really interested in the integrity of the internet, you probably take a serious look at what you're actually getting from your peers and upstreams. But the net police thing, it does impact regions where the domestic backbone is unavailable or costs a fortune compared with international bandwidth. I mean, this was especially true in South Asia. It was true in Australia until quite recently as well. I mean, a lot of the Australian ISPs basically would take the exit from the POP that they had, because the domestic backbone you could have with 2 megabit connections, and that was it. Because Telstra wouldn't give you anything else unless you paid them a fortune. So it caused problems because you get your /19 from APNIC, which you then had to dice up between your 6 points of presence, and then you had to announce the sub-prefixes, and you couldn't announce a covering aggregate because you had no way of connecting between your different POPs. The NetPlease stuff is also hard to maintain. I've probably told my Mongolian story in this forum before, but hey, what the heck, I'll tell it again. 2 years ago, I went to Ulaanbaatar to do a routing workshop because I got email from a couple of ISPs I knew saying, "Oh, Philip, we've got a bit of a problem. We seem to have bad connectivity to some bits of the internet." Well, I presume you know where Mongolia is. The country is sort of nestled in the top of China, so China's like this, and then Mongolia's sitting in there. It's like the eye in the middle of the face between China and Russia. So Russia's up above, China's below it, and Mongolia's in the middle. There are only two ways in. One way is through China, the other way is through Russia. So the Chinese connection is, well, through China. And we've all heard about the Great Firewall of China. So they were saying to me, we think it's the Great Firewall of China. We've been filtered because we can't get to CNN and blah, 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 and so on. And I said, well, what about through your Russian connection? Oh, well, the Russian one is no good. It's through the Siberian Railway and it breaks all the time with no idea what's happening. So it's like, okay, I'll do a routing workshop, teach you how to do all the multi-homing and so forth. So a few days in, I went to visit the one ISP and say, well, let's have a look at your BGP configuration. I'll try and see what's going on. I'm curious about this Great Firewall. So I had a look. And it's like, so I was like, can you explain what the configuration is? Oh, no, we don't know anything about it. What do you mean you don't know anything about it? Well, we got some consultant from the US who came in 1999 to set all this up, and he told us, don't touch it. If you touch it, it'll break. So they never touched it. Now, I went there 2005. This is 1999. What had happened? He had taken the IANA reserved address space and put it in as a BGP filter. Right? Now, 1999, if you think back then, IANA had just started handing out like network 62, 63, 64 to the registries, and that was about it. If you look back in 99, it was like the first use of 62, 63, 64. So it's basically 65 through 126 was blocked. And anything from about 206 upwards was blocked. So I said to him, okay, I think I found your problem. No Great Firewall of China, it's a Great Firewall of Mongolia. And we got rid of that, and surprise, surprise, CNN became visible. And through the Chinese connection as well. Because I knew the people inside Cisco who worked with the transit provider in China, and they confirmed that the transit traffic going through China was not subject to their content filtering. So, static filters are a really, really bad idea. So if you're heading off down the BGP path, do not ever, please don't put static filters in to block prefixes. If you want to do this thing, go to the good guys at Project Gumri or anybody else who's offering a Bogon BGP feed. Go to this URL, www.gumri.com/bgp/bogonrs.html. It will tell you how to set up an eBGP multi-hop BGP feed that will give you all the prefixes that should not be routed on the internet. And you can set up BGP with this, and basically you set the next hop pointing to a router that's basically a null interface, and any packets coming for those particular destinations or from those destinations will be dropped straight into the null interface. Whenever IANA releases a new block to the registries, the Gumri folks will update the Bogon BGP feed, and you have an up-to-date expectation of what you want or what you have on your routers. I know lots of ISPs who use this. I'm most surprised I find very few ISPs in the US and Europe who actually do this. Most ISPs who seem to use this are in Asia and the Pacific. I'm quite amazed how many of the Pacific ISPs are actually taking this Bogon BGP feed. But they actually seem to take it pretty seriously. Seems to be the people who've got really expensive external bandwidth are more keen to block any of this junk traffic than others. Anyway, so that's the NetPlease prefix list issue. Don't put in static filters. Okay, multi-homing scenarios. We'll take a look at some of this. A stub network is basically something like this. Stub network, you're sitting here, your upstream ISP AS100 is there. You've got two links going from your single router to your upstream single router. Yes, strictly this is multi-homing, but in reality what you do is you get the router just points two static defaults to each circuit, and the router will do per destination load balancing to their upstream. Okay, and that's very, very simple. So it works the same way, it's just a single static connection. You've got two, and the router will load balance to their upstream. Likewise, your upstream points a route to your address space along the two links, and it will load balance back to you. So you don't need BGP for this. You can use BGP if you want to, and there's nothing stopping you from using BGP. It will work, but there's really not much point. Second scenario is this one, multi-home stub network, where you've got two connections from your router, but your upstream has plugged them into different routers. So he's done the redundancy thing. This could be different points of presence, or could be different routers in one POP, whatever. Here you want to use BGP. Okay, you could use static routes with this, but you probably get pretty asymmetric traffic coming in because your upstream ISP's got no way of really balancing load between the two external paths. Whereas it's very simple. You just point two statics and it'll do per destination load balancing on the two paths anyway. But statics is really not a wonderful idea. As I say, it will work, but it's not really a lot of control. Use BGP for this. Perfect example of a situation you can use. AS65530, private AS number. You will not get a public AS number from the registries to do this. It has to be a private AS number. So pick one that works. Anything above 64511. Use BGP. Do not use OSPF, or ISIS, or RIP, or EIGRP, or any interior routing protocol. You're running an interior routing protocol in there. These guys no doubt will be running our interior routing protocol as well. Chances are they will be the same. And guess what? If you run OSPF here, OSPF there, OSPF in between, you end up with your prefixes bleeding into each other's networks. This is really not a good idea. Okay? So try and really avoid that situation. I won't tell you the story. This happened to me, so that's why I say try not to do this. I mean, I didn't do it, it was other people who did it, but anyway, you come back from holiday and you see 2,000 extra prefixes in your IGP and go, oh, what happened there? I didn't know our network quadrupled in size over 2 weeks. So don't run IGP in the external or the demarcation zone here, right? The I in IGP stands for interior. Interior means inside. Inside is not outside. Easy way of remembering. Okay. This situation,
I have one question. In this case, or well, in the previous case, exactly. Will the BGP announcements from this AS 65530 be visible outside the autonomous system 100?
No, it won't be visible.
Just for their
It's just inside here, because what he will do is, on his eBGP, he'll use remove private AS, and so it'll look as though AS100 has originated the address block from there.
I think that external visibility comes in your next scenarios, right? When
Yes.
you have to multi-homing with different ASs.
Yeah. I mean, I've got worked examples of this thing. I'm just introducing the concept at the moment, but I've got actual worked examples that show you how this actually works in real life. Yeah. I mean, if this link breaks, for example, the configuration have shows you how to work around that. Yeah. I've got configuration examples for all of this, so don't worry, it's all coming. So this is the other situation. Here's a sort of true multi-home network. AS100 here's got, say, 2 links to AS200, and it's got a single link to AS300. So the two upstreams are 200 and 300. They connect to the global internet somehow, and you need to multi-home. And I mean, there's no simple answer to trying to solve this thing. You can't just do the router BGP neighbor multi-home command. It doesn't exist. So you've got to sit down, understand the 4 attributes that you can play with, and then figure out how to deal with them properly. I suppose it's a little bit like learning to juggle. When you learn to juggle, you're given 1 ball, and you get that configuration sorted out first. Then you're given 2, and then 3, and then 4. A juggler will not give you 6 balls to say, here, go learn to juggle. Here, start with 6, that's easy. Right, so we start with something nice and simple, and we build it up to something like that. Okay, multiple sessions to an ISP. Example 1. Well, if you've got something like this, you're sitting in here, upstream is there, you've got 3 links between you and your upstream. How do we do BGP here? Well, see, for this case, there are lots of things you can do. You can point 3 static routes on the links. That's all fine. If you're brave, you can do multi-link PPP and get the routers to bond the 3 circuits together. You can get a MUX and make it presented as one circuit, or you can use BGP like this. And this is eBGP multi-hop. And what this will do, eBGP normally, from the last presentation, eBGP normally runs on point-to-point links, right? Directly connected connections. Whereas iBGP, generally ISPs will set it up between loopbacks. You don't run iBGP on direct connections. Okay, eBGP you run on direct, iBGP you run between loopbacks. So, but this is going to be slightly different because you've got 3 links here. So how do you run eBGP on the link? Well, you can run 3 different eBGP sessions. But if you're trying to handle the full BGP table, it gets a little bit of a handful, as you'll see in coming slides. So what the people tend to do is use eBGP multi-hop and between the loopback addresses. So we run eBGP between this loopback and that loopback. What that will mean is we point static route for each loopback, well, for the loopback to each of the serial interfaces. So this loopback is reachable through serial 10, 11, and 12. Okay, so we've got 3 static routes pointing to the remote loopback, and then we've got neighbor 111, remote AS200, eBGP multi-hop 2, which tells eBGP basically we're not going to be directly connected. We expect TTL 2 coming in. Okay, so we're going to expect up to TTL 2 coming in. If it was directly connected, it would be TTL 1. Right, so this is the example of when you would use eBGP multi-hop. It's the only example of when you'd use eBGP multi-hop. Seems to be current vogue that people set up eBGP sessions with eBGP multi-hop by default. Well, you can do that if you really want to, but it's actually really dangerous to try and do that. A lot of the people who seem gung-ho about configuring eBGP multi-hop for everything don't realize about this, well, I've called little gotcha, but it's actually a major gotcha. If R1 and R3 are doing the eBGP multi-hop peering, well, you configure that with eBGP multi-hop too, because it's 2 hops away. Okay, a hop from there to there is still TTL2 as is there to there, TTL2. If this link breaks, the eBGP session can maintain that way. When I remember situations from my past where we've set this up for customers and they have no idea that the main link has gone down and the tiny little backup circuit is all that's carrying the traffic. And it's about a month or 2 down the path that they've complained to us, oh, your internet is really, really slow. And we go, no, it's not. It seems to be working really fine. What's happening? And what's actually happened is that the main link has gone down. Of course, we don't monitor the circuit for them because, well, they didn't want it to be monitored or they didn't provide us any means of pinging the other end of the link. But they're running eBGP multi-hop, and of course the main link's gone down. They haven't watched that the circuit's gone down, and they're using this skinny little backup as the backup, or the main path for traffic. So eBGP multi-hop is actually really dangerous to use. In fact, you get to the situation where I would just say try and avoid it unless it's absolutely necessary to use. In the main situations for load sharing across multiple links, or if you're going to provide, say, a BGP feed, for example, receive one from the Bogon route server, or provide a BGP feed to something like RouteFuse. That's about the only time you want to use eBGP multi-hop. Other examples, if you've got a satellite connection, obviously satellite modems aren't very good at talking BGP, so you want to try and do multi-hop for that type of thing. But otherwise, that is about it. Yeah. 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 Yeah, I mean, see that anything where you've got like multiple connections between 2 devices, eBGP multi-hop is probably a nice solution. Whereas trying to do the link aggregation at layer 2 level, as I say, that's why I've been burnt a lot by MLPPP, multi-link PPP on serial connections, and I imagine Ethernet link aggregation could end up going the same way. I don't have experience of that, but I can imagine the same difficulties there. Yeah, I would say so. I mean, I actually got this quote a few years ago from one of the tier 1s, the real tier 1s, and they said this: they will run it, but they will not support it as a standard offering. So their customers basically have got to go and beg and sign agreements that they're not going to blame them for problems and so forth if anything breaks. Which I find it's almost the opposite of some other ISPs who pretty much insist that it's eBGP multi-hop, even when the router speaking BGP is another end of the point-to-point link. And when I point out some of the things that go wrong, they said, oh, that's just our standard practice. It's like, well, why? So, anyway. The main issue, the main things that can go wrong is because what people tend to do is that eBGP speaking router is not on the edge of the network. It's somewhere buried in the middle of both the upstream ISP and the customer. And then the connectivity between the eBGP multi-hopping routers goes wrong somehow. It could be static routes or something pointing in the wrong direction, or routing information that's bad or not converged or something like that. It will break the eBGP session. So you really want to try and avoid that as much as possible. So after my warning about eBGP multi-hop, really try not to do it unless there really is no other alternative. BGP multipath. Well, this was the other alternative to eBGP multi-hop, which I thought was pretty cool many, many years ago when it first appeared. But as I said a few minutes ago, we've got the full BGP table, 234,000 prefixes, and something like this. It means you end up with a huge number of paths on the router. Okay, 700,000 plus paths. So, I mean, what it generally will do, it'll put 3 parallel paths in the forwarding table. So again, your router will load balance over the 3 parallel paths. It was meant to be a cheaper way than trying to do 3 static routes to remote loopbacks and then eBGP multi-hop. Getting BGP to put 3 paths in the forwarding table. This kind of thing, multiple sessions to an ISP, well, this applies to all multi-homing. The simplest scheme is always to try and use defaults. It's always best to use defaults wherever you can. And a lot of people sort of heading off down the path, as we'll see in the second half, of, oh, multi-homing, we need full BGP table. And that question is, why? What does it give you? Why is it different from a default? I mean, it's generally not different from a default. So the simplest scheme is always to use defaults. Then you learn and advertise prefixes for better control. That gives you your fine-tuning. Okay, learn prefixes or advertise particular prefixes to give you better control over your load balancing. It does need planning, and it does need some work to try to actually get the load balancing that you need. The important thing to remember is that there's no magic solution at all. So really the rest of the presentation is going to be covering a lot of situations about how to do all this, where to start, what needs to be done. Now, where are we for time? We finish it. Yeah, 3 is the first break. So the first bit I want to run through quickly is preparing the network. I'm not going to spend a huge amount of time on this, but it's really assuming that you're starting off with no routing whatsoever. Okay, you've got a few routers in your backbone. You're using just static routing to connect everything together. It's the usual thing if you ask a question on NANOG about, hey, what routing protocol should I use for my backbone? You'll get, well, you get all the ISIs people saying ISIs, you get all the OSPF people saying OSPF, and then you get 1 or 2 other people saying, hey, use static routing for your backbone, it works for mine. Okay, so don't ask weird questions like that on NANOG because you'll get the answer you deserve, more or less. Everything is possible, it's just whether it makes sense or not. So what I'm going to do is I'm just going to step through the basic things you need to get away from static routing for your backbone. We run an IGP, we get IBGP running, and then we're ready to go and do eBGP. If you're going to multi-home to different ISPs, you need a public AS number. So you go to your upstream ISP, if they're a member of the registry, get one from them. They can do that. Apply to the registry yourself for a one-off assignment. You can do that too. Ask an ISP who is a registry member. You can do that as well, because ISPs or registry members can get AS numbers for their customers. Even though your only relationship with that ISP is the AS number customer, you're still a customer. Okay? And the final one, which is the best one, is join the registry yourself and get your own IP address allocation. This option is actually strongly recommended because it becomes really simple to do multi-homing with your own address space. Multi-homing with other people's address space is really hard, especially when your upstream ISP makes you sign things that says, I will not, or I promise not to announce your address space to anybody else. Okay, so some ISPs will basically say, if I see you announcing my address space to anybody else, I will disconnect you. And that's something they seem definitely wanting to do. I think they've got the theory that, well, if they announce it to somebody else, then they might lose them as a customer. Can't quite see how that works myself, but anyway. But anyway, seriously, joining the registry is the best thing to do. Joining fee is not that much. Compared with buying even a cheap router, it's still a very, very simple way to do things. And with that membership fee, you can then apply for your address space, V4 address space, your AS number, your V6 address space.
How do you deal with the problem with IPv6 where you can't get an allocation directly?
You can.
Only ISPs, right? Not end users. And they'll give you a /48 because I was just looking online. I didn't see that anymore.
Yeah. But I mean, again, as I say, I mentioned downstairs, the three solutions: go to the registry. You can go to your upstream ISP and get a /48 from them, or you can use 6-4, which is a much overlooked way of doing stuff. I mean, I've been using 6-4 for about 6 years now for my home network, and I've got a /48. That's a routable V6 /48 based on my single /32 V4 address I get from my ISP, who has never ever heard of V6. But anyway, I mean, but this is the whole thing. And okay, I'm sidetracking. What is an internet service provider? I'm quite amused that some people actually trying to define what an internet service provider is. I mean, internet service provider is somebody who provides internet services to a group of customers. So, as far as I'm concerned, Cisco's IT department is an internet service provider because, hey, they're providing internet services to the whole global company, all the different business units, all the different sales offices, all the different corporate functions, all the different every other functions. I mean, they are all separate businesses. Hey, and we all pay for our internet access in the internal money changing hands thing. So they are an internet service provider as everybody else is. That may not meet the definitions of some people for an internet service provider, but they sure as heck meet my definitions. You know, the same questions came up last month in Durban in the V6 routing workshop I was doing. Oh, but we're a university, we're not internet service provider. What, I mean you're a university with just one department? Oh, no, we've got 200 departments. Well, you're an internet service provider. You're providing internet service to all the different departments. Go and apply for your V6 addresses. I don't know if they have or not yet, but I mean, that was it. They are an internet service provider. It just may not be a commercial, publicly listed, blah, blah, blah internet service provider, but they're still providing valid internet services. Anyway, so that's my personal rant stroke sidetrack. Right, preparing the network. Well, the network is not running any BGP at the moment. So we've got a single statically routed connection to the upstream ISP. We're not running any IGP either. So static default and routes through the network to do the routing. You'll be amazed how many really big ISPs are doing nothing but static routes. And they don't understand even how an IGP will bring them any benefit. So moving these guys over to OSPF or ISIs is always quite entertaining. So first thing, pick your IGP, OSPF or ISIs. Do not ask on NANOG which one you should use. If you do, you'll get people refer you to Dave Katz's presentation back from about 2001, which compares the merits of OSPF and ISIs. And I think if you look at the last slide, he pretty much says, yeah, pretty much the same. Okay? So it's really down to personal choice. So if you hired somebody who used to work at Sprint or UUNet, for example, they'll probably implement RSIs. If you hire somebody who's come from somewhere else, maybe from Europe, they're probably going to implement OSPF. That's really kind of what it boils down to. You then assign loopback interfaces and /32 addresses to each router, which will run the IGP. So loopbacks mean that we've got your router ID anchor, you've got your IBGP point, so you run IBGP between the loopbacks, of course. Any routes that you originate into your backbone that are going to be used by your customers will have the loopback address as the next hop address, so that'll all be quite nice. You then deploy your IGP. For example, OSPF, for sake of argument. It will have no impact on the existing static routing because the OSPF distance is 110 in iOS, static route distance is 1 in iOS. Well, static distance of 1 will always beat OSPF distance 110. So you can deploy OSPF and not break anything. And I've had all these people over the years who do not believe me that this is possible, and I go and deploy OSPF for them, and of course the network still just works. Because the static route distances, if your network already works with static routes, OSPF is not going to break it. Okay? It just works. So smallest distance wins. So that's easy. You can deploy OSPF like that. Notice we're not pulling out any of the static routes yet. We're just deploying our IGP. Be prudent deploying IGP. Keep the link state database lean. In other words, only put router loopbacks and the WAN point-to-point links in OSPF. In fact, anything that is going to use dynamic routing on it, put in OSPF. Everything else you dump into your IBGP. Try and do summarization on area boundaries or level boundaries if possible. So try and come up with a sensible IGP addressing plan as well. Okay, just to anything to keep the number of prefixes in area 0 as low as possible is a good thing. So routes which don't go into the IGP include dynamic assignment pools. So you've got DSL, cable, dial, wireless. All these are dynamic assignment pools. All these addresses are going to be used by your customers. Stuff those into IBGP. Don't put them into your IGP. Don't put them into OSPF. Customer point-to-point link addressing. Well, if you're going to monitor your customer point-to-point links, the best place to do put these is put them into IBGP. Okay, you've got all these /30s, put them into your IBGP, so at least your NOC can monitor the point-to-point links. If you don't care about monitoring your customer links, then simply use next hop self in IBGP. And what that will do is, rather than using the point-to-point link, external point-to-point link as the BGP next hop, you end up with a local loopback interface address as the next hop. And that means fewer prefixes to carry in your IBGP as well. Don't put static or hosting LANs in there. Okay, you've got a big hosting LAN with lots of devices. Don't put them into OSPF. You're not running any routing protocols down there. Customer assigned address space. Any address blocks you give to customers, don't put them in OSPF. Stuff them into IBGP. In fact, anything else you can think of, don't put it into OSPF. Right? There's really very little should go into OSPF at all. So that sort of configuration, well, okay, I've set up a loopback interface, /32 mask for the address. Ethernet, here 2 customer connections, that's our LAN, whatever. And then we set up OSPF network statement. So this is the loopback. Pop the loopback address into OSPF. And then the network statement for the LAN. So that goes into OSPF as well. Passive interface default means we're not going to chatter OSPF out any of the interfaces at all. And then we do no passive on Ethernet 00, which means we're going to find OSPF neighbors out of Ethernet 0. Again, I have no idea why this is not default in iOS, but it should be, because again, visiting so many ISPs, I sit there at an ISP and I see all these OSPF hellos coming from the upstream provider. And I'm always sorely tempted just to bring up an OSPF to talk to the upstream and feed them lots of junk, because that's really the only way to get them to stop doing this. And when I send them emails, or at least get the ISP I'm working with to send an email to the upstream saying, hey, you're sending us OSPF hellos, please stop. They come back with weird sort of answers like, we're not, or none of your business how we run our network, or, well, if it's a problem, put a filter in. And it's like, it's all kind of stupid answers. And it's like you're pointing out a misconfiguration and people come back with really dumb responses. So do the right thing, mark all interfaces as passive, and do no passive on the interfaces you actually want to talk OSPF out of. Okay, so the red is really what you've added to the existing static routing on this router. Now, let's have a look at IBGP. Second step is doing that. IBGP can run on all routers in the network, or a subset of routers, or just on the upstream edge. Now, there are lots of choices. The main thing is you want IBGP to run on the transit path. That's pretty important. If you have routers A and B only talking IBGP and the link between them breaks, well, the only way that A is going to get to B is to go to router D. How does router D get to, well, router B? You have no idea. And okay, it might have some idea, but if you're trying to get to a destination that's visible through B but not visible through A, well, A will say, okay, well, the best path is next hop is router B. How do I get to router B? I go to D. D is asked, how do I get to this external destination? D goes, I'll just follow the default route, which might point back to A, and you end up with a routing loop. Okay, so that's pretty important to be aware of. You want to run IBGP on the transit path at least. And all these routers on the network are on the transit path. So you pretty much want to run IBGP everywhere, so that you have a full view of what's going on everywhere. This case, only A, B, and D need to run IBGP. Routers C, E, and F don't need to because they're on the edge. But quite frankly, I run iBGP everywhere on the network because there's virtually no routing devices these days that can't run BGP. And those devices that can't generally are pretty dumb aggregation devices that you can usually proxy by a proper aggregation or access router anyway. So you generally want to run iBGP everywhere. So typical service provider network has 3 layers in it. Some have more, some have less. You've got the core layer, which is the backbone, usually the transit path. Distribution layer, where all the aggregation of the different points of presence is done. And then you've got the aggregation layer, which are all the devices that are connecting the customers to your backbone. So some ISPs don't have a distribution layer, the smaller networks, but you generally very, very visibly see a core and an aggregation portion. Now in the aggregation layer, iBGP is optional, but many ISPs just run iBGP here, right? It's pretty much easier to run iBGP everywhere across the backbone than trying to do it in pieces. Okay? People either run partial routing, which is most common. Some people run full routing as well. Partial routing basically means the prefixes within your iBGP. So you don't take any prefixes you learn from outside your network and dump them into iBGP. You don't want to carry all 234,000 prefixes within your iBGP unless you want to give them to somebody else. And if you want to give them to somebody else, well, you probably want to charge them lots of money for the privilege, because 234,000 prefixes on routers is a fairly serious amount of real estate needed for that. I mean, yes, there's all this hand-wringing about Supervisor 2's finally running out of fib space a few weeks ago on the NANOG list. And it's like, well, why on earth are people carrying 234,000 prefixes on a switch? I mean, it's basically an Ethernet switch that's got a layer 3 aggregation function in it. And, you know, it's well known that it was never really intended to be a core router, so why on earth are people trying to do that? Okay, that's probably not politically correct to say it as a vendor, but I'm still left scratching my head trying to think why people are designing the network that particular way. Well, I mean, it's not even has to be that. It's the main thing is, you know, Supervisor 720, to get into specifics, is the modern one. The Supervisor 2 is ancient, and at least the 720 can handle. Oh, I might get this wrong. Is it 1 million entries in the fib? I think it's that. Depending which, yeah. It's 256 as well. Okay. Right. Okay, so it's a 3BXL will handle big numbers. Okay. Yeah, or the 3CXL, yeah. But this is the thing. Think hard where you're actually going to carry the full BGP feed. It's only really the core routers that are going to need to do this. Pretty much anywhere else shouldn't really have to. If you've got a customer who wants a full BGP feed from you, I mean, the thing that we did at UUNet was we set aside a special router, which we connected them to. Okay, in the POP, every POP where we had a customer who wanted a full BGP feed, they connected to that special router that had big memory. Okay, in those days it had 128 meg of memory rather than 32 meg memory. But at least, you know, it was a special router, and they got a special price from us. Okay, it was slightly more than the standard, well, default or iBGP feed that they would otherwise get. Yeah, we kind of followed what Sean Duran was saying way back all those years ago. If your customers want full BGP table, charge them money for it. What else? Oh yeah, so making the partial routing bit, it's pretty easy to do this, because the way you do it, I mean, I haven't got any configurations. The way you do it is you just tag your internal prefixes in one community, the externals in another one, and only announce the internal prefixes to all the routers within the iBGP. And that way, it keeps it nice and separate. There's some aggregation devices that still can't run iBGP. I would say don't buy them, but I'll probably regret that. It's probably a case of more just point static routes to them for the address pools that are being used on those boxes from the nearest BGP capable router, and then just use IGP for the nearest exit. Distribution layer, pretty much always run iBGP here, otherwise it just gets too complicated trying to handle the aggregation to distribution part. It doesn't have to do it, but really it's not worth going down this path. I mean, if you're going to deploy something in your network, just deploy iBGP pretty much everywhere. So if you're going to grow large, just deploy the iBGP. It's like minimal overhead, it's no hassle. I say, running BGP is nothing to do with the size of chassis that you've got. It's whether it's there in software or not. In the many parts of the internet, they're using routers that we haven't seen here in North America for probably a decade. And they're still working just fine. Core layer is the transit path, IBGP you need between core devices, 4 routes if you're a transit provider. If you're not providing transit to any other autonomous systems, you can get away with partial prefixes. Given there are only about 2,500 transit providing ASs on the internet, it's only 10% of the internet really needs to carry the full BGP table in the core of the network. So we decide on our BGP policy. Are we going to do full routes everywhere, or partial, or some mixture? What are we going to do with core layer, distribution, aggregation layer? What about our scaling techniques? What communities are we going to use inside our network? Are we going to use route reflectors? The answer for that was probably yes. Are we going to use any other labor-saving devices? I mean, okay, iOS has got peer groups, peer templates. Junos has got some other stuff. iOS XR's got some other stuff again. Use any of these labor-saving devices just to make bringing up the BGP mesh quick and easy. And then you deploy it. Yes, you can deploy BGP without breaking anything, because BGP on iOS has a distance of 200. 200 is a lot bigger than 1. 1 is a static route. If your static routes all work, they will override anything you hear by BGP, if it's done properly. So step 1, introduce the iBGP mesh. So do your route reflector thing, whatever. Make sure the iBGP distance is greater than IGP, which it usually is. It's probably worth checking your vendor. I mean, iOS at least is iBGP default distance is 200, which is a lot greater than the IGP one of 110. Install the customer prefixes into the iBGP. Make sure your network still works. It should. Things should not have broken. Okay, I mean, I've done this so often for many ISPs that I know this generally works. So things should still work fine. The big deal is step 3. Carefully remove the static routing for the prefixes in the IGP and the iBGP. It's pulling out the static routing across your backbone is where things really can go wrong. So you don't sort of dive in and do the whole network all at once. Start with a friendly customer. If you've given your staff home connections, maybe DSL or something like that, well, play with them first. It doesn't matter if the home connection doesn't work so well. What are they going to do? Are they going to charge you for loss of service? No. They're just going to come to the office more. So you can test them first to see how things actually go. By putting customer prefix into iBGP, I mean all the address space you give to customers. So you have a network statement, point the static route towards the customer, use a unique community to identify customer assignments, point-to-point links you may want to put into iBGP as well. Put them in a special community that only gets announced to your network operations center. So if they want to monitor customer point-to-point links, then they can see those. You don't need to distribute the /30s to everybody else across your backbone, just to your NOC. Dynamic assignment pools, local LANs, all that kind of thing goes into iBGP. Removing the static routes, pick on one router at a time, pick on one customer on that router, make sure he's all happy, do the next one. Once all that router's done, fine, leave it for a week, see if anything breaks. Move on to the next routers in the POP, leave it for a while. Once everybody's happy, move on to the next POP, and so forth. I mean, don't do the mass migration in like 1 hour flat. Try and spend a bit of time to phase it. If you pull together a plan based on this, it should just work fine. Okay, so they're not really Flag Day steps, just plan it all properly and it'll all work great. So I will start the next bit just before we have the coffee break. So we're really having a look at some of the basic multi-homing. So it's going to look at basically no frills. It's going to be very, very simple cases. Multi-homing to the same ISP, then going to the different ISPs, which will be after the coffee break. And then we'll go on to the more detailed type of multi-homing a bit later on. Going to keep the example simple. Each example will assume that the side has got a /19. When I first wrote these slides, that was the registry allocation size. Of course, it's all changed since then. I haven't really changed the examples. There's no real need. It doesn't matter what address block you're using for this. Although /24 could be a bit hard. But at least the /19, 20, 21, all these examples will work equally well. So this basic multi-homing, this is common at the edge of the internet, where the bulk of your traffic is coming into your network. Your outbound traffic is probably 30% in volume compared with incoming, so nearest exit is usually enough. Later on in the afternoon, we're going to look at well, trying to do outbound traffic engineering and what you have to actually do there, which is more of concern for people who are closer to the center of the internet, or who are providing transit, or who are content providers who generally have more outbound traffic than they have inbound traffic. Okay, multi-homing to the same ISP. We need to use BGP, of course. We need to use a private AS number. So here what will happen is your upstream ISP will generally tell you what private AS number to use. I mean, you could make one up, but you'll have to agree with your upstream, obviously, in what it's going to be. Okay, generally you'll find that your upstream says use AS blah. Because you see a bit later on, if the upstream has got lots of people like you who are multi-homing onto their backbone, they're going to set up maybe peer groups for economies of scale. The upstream ISP will proxy aggregate. In other words, they'll announce your address block to the internet from their AS number, just as though you had a simple static connection to them. Now, the first example we're going to look at is making one link the primary path and the other one the backup. So, for example, primary path could be an E1 2 megabit circuit. I mean, I'm just using European circuit sizes rather than North American circuit sizes because, well, the first time I wrote the slides, I was actually sitting in Australia and they don't know what T1s and so forth are. So, so E1 primary path 2 meg, backup is 64K connection. It's not realistic in real life, but I'm showing you a particular scenario. I mean, actually, it's semi-realistic in real life because one time I was away on holiday from UUNet, our sales guys cooked up this wonderful service for us to go and implement. And it was like 2 meg with a 64K backup. And they thought this was a wonderful service to offer. And when I asked them, said, well, okay, how are we going to squeeze 2 megabits of traffic in a 64K link? And it's like, look, I'm sales. You're the techies. You make it work. So I'll show you as an example if there's anything like this. So what do you want? You want the A to C link to be the primary path, the B to D link to be the backup path. AS65534 we've chosen. AS100 is upstream. What we do is we announce the /19 aggregate on each link. This is really, really important. Always announce the aggregate on every external link. If you announce your aggregate, it basically means if one path breaks, because you're announcing the aggregate out the other path, you get automatic backup. Because many people who try and do multi-homing can't get this simple bit right. And they say, oh, I've got it all configured as you said, but they miss one thing, announcing the aggregate. Right? So if you announce the aggregate on each path that you have, then you will get backup. If one link fails, you will get backup out the other path. So outbound, you announce your /19, and just announce it. Simple as that. Inbound, we accept the default route. That's all we need. Default route says, I know how to get to the whole world. That's what it means. The default route takes the place of 234,000 prefixes that your upstream ISP is no doubt carrying. Okay, so that's simple. What about the backup? Well, we announce the /19, but we increase the metric. Remember, lowest metric wins. So we're sending the /19 out with a standard metric, which is 0. Okay, absence of metric, or you can set metric of 1 to be absolutely sure. Default metric is 0, so this /19 arrives at your upstream with metric 0. This one arrives at upstream with metric something bigger. This becomes the backup path. So your upstream provider will use this link for inbound traffic. Now, on the inbound announcements from your upstream, you also get the default route here, and you reduce the local preference. Default local preference 100, just make it lower, 50, 60, whatever, and it becomes the backup for outbound traffic. Question? So that will be taking the metric you hear from another provider and sort of popping it into the IGP. Yeah. Yeah. I haven't seen that in any of the providers I've looked at, but I mean, it's not to say it doesn't happen. So yeah, if you do that, then that's useful. Because I mean, I know that some ISPs will take the IGP metric and convert that into a BGP metric for their upstream provider to then do the inbound balancing properly. So I sometimes see that happen as well. The other thing that I do see happen quite a bit is that ISPs don't support metrics at all. Certainly those who've been around for longer, because RFC 1771 days, well, that RFC didn't actually define what absence of metric meant. So Cisco said, oh, well, if there's no metric, we'll say the default metric is 0. And Wellfleet in those days said, oh, well, if there's no metric, we'll make it 2 to the 32, I think it was -1 or -2, something like that. So if you used metrics and you were in a Cisco network connecting to a Wellfleet network, their idea of a default metric was very different from your idea of a default metric. So you ended up with weird stuff that you really didn't quite expect. I think it was Curtis Willemeiser that did a presentation a long, long time ago at IETF showing a problem between IBM routers and ANS network, and I think it was UUNet using the Cisco routers. But that's dim and distant past that I'm trying to remember now. But there was an issue there as well. So you find a lot of ISPs will not support metrics at all. So if anybody sends a metric, they basically slap a local pref over it.
Why wouldn't you use backpack instead of metric 2?
Yeah, you can do that. But I mean, let's see, I'm keeping a nice simple example. This is an example of where you would use metric. You know, ignoring all the badness happening out in the real world, in the ideal world, this is how you do it. I mean, yes, I've got the AS path prepends coming up when you multi-home to different providers. I mean, that's coming up later on. And yes, you could do the same thing here, and that would work perfectly well also. Okay, so configuration of this, so router A, this is the primary path to the upstream, so we've got a /19 there. Prefix list aggregate out, prefix list default in. Well, this is actually quite straightforward to do. And you've got your static route to null, which injects that into the BGP table. Okay, so it's not exactly complex. And this is actually real working configuration stolen from the templates that we used to give our customers back in my UUNet days. I've just put some numbers in there by example. We basically had a Perl script that took the basic template there and popped in the addresses that the customer had, and was, dear Mr. Customer, here's your BGP configuration. Put it on your router. Customers all got excited because they could do BGP without knowing anything about it. Router B configuration, this is the one with the backup. So again, prefix list aggregate out, default in, and then we've got a route map out and a route map in to apply our policy. So the route map out, what it does, it says if the prefix going out is the aggregate, we set metric to 10. And that's pretty much all it does. Route map router D in basically says any prefix coming in, we set local preference to 90. The only thing that's coming in from the upstream is a default route, so we set local pref 90. That is lower than the default of 100, so this becomes the backup for outbound traffic. Okay? So that's how you do primary path, backup path in this case. Look at the upstream. This is where the upstream is happy because he gets economies of scale. Router BGP, remote AS65534, he does the default originate to send the default route to the customer. Prefix list customer in, prefix list default out. That's all he needs. Customer address space, accepted inbound, he sends the default route out, and that is all. He doesn't care which path the customer is using as primary or backup. So if a customer wants to swap them around, can't see why he would, but if he did want to swap them around, he doesn't have to phone the NOC and say, hey, can we change the configuration? I want to change what is primary and what is backup. Because router D is the same. Okay, same configuration. Okay, service providers, transit providers do not want to have custom configurations for customers. They want standard configurations, because then the configuration templates, the provisioning systems can make nice, simple, standard configurations. They don't want to have custom configurations per customer. Router E, this connects to somewhere else, so from AS100 to the outside world. Strip out the private AS, so there's the remove private AS command. Prefix list customer out, for example, has the 121.10/19 customer address space. So as far as the world is concerned, it sees 121.10/19 originated by AS100 because the private AS gets stripped out. So this one, I was saying, the previous example using primary path, backup path is probably not very realistic. You tend not to buy one circuit and then just leave it idle. You end up with the usual case of, okay, all your traffic is using the primary path, and you don't actually notice that your backup has gone down, so when you actually want to use your backup, it ain't there. See, that happened to us more than a few times with our servers that I was talking about, where we had the primary E1 backup 64. We didn't actually monitor the 64K link, and of course when the E1 went down, guess what? The 64K hadn't even been there. It'd even been a couple of times it was deprovisioned by BT because, well, we weren't using it, or they made a mistake or something like that. So, as I say, it's not very realistic, but at least it shows you how to do the primary backup concept. So what I want to show here is a more common case where you're going to try and balance traffic on both paths. Now this is assuming equal capacity circuits. It's not completely realistic, but again, it just shows you where you would start trying to do anything like this. So the link between A and C is going to be the first link, B and D is going to be the second link, same private AS, same /19, router E is going to do the announcement out to the wider internet. So as before, we announce a /19 on each link. That gives us the backup. So if one link fails, because we're announcing the 19 on the other link, we get the backup. Our upstream provider sends us the default route on both links as well. Okay, so that gives us the backup in case one link fails. And then, after that, well, we split the 19 and announce it as two 20s, one on each link. So what that will do is you send 120 on the A to C link, the other 20 on the B to D link. So we're taking the /19, chop it into two pieces. What this basically does is you get half the traffic going on one link, the other half of the traffic going on the other link. Basically anything destined for the first half of the address space comes in one path, and anything destined for the other half of the address space comes in the other half. Okay, this is very naive because you never get a situation where traffic to each IP address is the same. Okay, there's going to be some kind of well, hotspots within your address space, but this is just showing you the basic how we start doing this. Do the first subdivision, see what happens. Okay, so we chop our address space into two, one half out one link, the other half out the other link, and then see what we get. It may not be perfect load balancing, so we then have to vary the split until we get the perfect load balancing that we're after. So the configuration for this is, well, we're generating a /19 aggregate there. There's the static route to match it. We've got the first /20 sitting here, the static route to match that. And then the peering with AS100. Outbound, we're sending the 19 as well as the first /20. Inbound, we accept the default route. Okay, so that's fairly straightforward. Router B has exactly the same configuration, but for the other /20. So it'll be 121.10.16 there, and it'll be 121.10.16 sitting there. Okay, so you do it for the other half of the address space. Okay, remember, a /20 will always override anything that's, or traffic for the /20 will always override anything for its parent /19. Right, it's more specific, always wins. Router C configuration, again, the upstream provider doesn't really particularly care what you're going to try and send on the link, as long as the addresses come from your address space. So you tend to see that they do default originate to send you the default route, outbound to send the default, inbound to accept just your address space. So you have something like permit 121.10/19 LE20, which means out of the /19 address space, allow any prefixes sizes less than or equal to 20. In other words, it lets the /19 through or the two /20s through, and anything else will get dropped. In fact, you find these days that some ISPs just do /19 or whatever LE24 to allow all prefix sizes down to a /24. And that way they don't particularly care what the customer is doing for load balancing on the link to them. Okay? So that's how we do this one. Router E configuration, again, we remove private AS, strip out the private AS. Prefix list customer out, we only let our customer aggregate out. We don't let any of the traffic engineering prefixes out because they give no further information to the internet. All right, so that's important to remember. Some ISPs just basically don't have any prefix list here at all, so they let anything go out, so including all the sub-prefixes for the local traffic engineering. You don't need to do that. Okay, you simply just let the aggregate out, and that is sufficient. What about the default route for outbound traffic? Well, what you can do is just use nearest exit. Simple way to do that is just pop the default into OSPF. This says, well, the OSPF process, originate the default route, do it with, well, metric 2, metric type 1. I suppose the last two things are optional, but certainly default originate basically says, if you see the default route in the routing table, we drop it into OSPF as well. And what that will do is we get a much better way of handling a default within our own network. Nearest exit is usually sufficient. We're not doing any of the outbound traffic engineering here yet. Notice the load sharing configuration is on the customer router. So the customer is not happy with the load balancing. You can say, dear Mr. Customer, if you're not happy with it, you fix it. You have the tools, because the upstream ISP just has standard BGP configuration and a filter that lets any of the prefixes and the aggregate into their iBGP. So you can give the customer a little bit of power to actually do their own load balancing. Note with this, you could also use BGP communities to do it. I'm not going to cover communities until right at the end, but you could also use BGP communities to do this sort of thing. Okay, I promised to talk about RFC 2270 a little bit, so here we go. It's unusual for any ISP to have just one dual-homed customer. Generally, if you're going to have dual-home customers, you're going to have lots of them. So let's try and standardize the service offering and the configuration a little bit. This all came, RFC 2270 was written by the guys who basically were running Internet MCI's backbone all those years ago. And quite a few other people I know actually adopted this as well, as it simplified a lot of their configuration. What you're doing is looking at trying to scale the configuration. That means simplifying it for you as the transit provider. Every customer ends up basically having the same configuration. So we're sitting here AS100. We've got lots of these customers all multi-homed onto our backbone, and so we can simplify things. Each router A and each router B gets the same configuration, modular the address space being used. So all sitting in the same AS number, all got the same type of prefix filters and so on. Customer announcements are the same as the previous example. Okay, so it's the /19. You announce the 19 aggregate in each link, subdivide 2/20s or 21s or 22s or however you need to go to get traffic balance on each link. We're using the same private AS because what we're doing is, as the upstream provider, we're sending just a default route to our customers. Right, the customers receiving a default route, it basically says to them, look, we know how, here is the full internet routing table, but we're representing it by one prefix. So we don't have the duplicate or the AS path loop detection problem, because you're not going to see specific prefixes from one instance of AS 65534 inside another AS. So we can use the same AS for each thing, which just makes things simpler. Of course, we don't have overlapping address space. And you can't really have overlapping v4 address space, so that's not a problem either. The router A1 configuration, well, it's the usual stuff we've seen before. BGP 65534, the /19, and a sub-prefix, the outbound prefix filter, etc. It gets interesting when you look at the upstream provider. So router C, because we're going to try and make this scale, we set aside a peer group. Everybody's in AS 65534. Everybody gets a default originate. Everybody sees just the default route outbound. So we stuff that in the peer group, and then we use the peer group for each neighbor going onwards. So customer 1 belongs to this peer group, still has a separate inbound filter. Customer 2, same thing. Customer 3, same thing. Customer 4, 5, 6, 7, 10, 15, 20, and so forth. Okay, you can all have the same configuration. And then you have a prefix list which applies for each customer. I've made it 19LE20 there. In the common cases, you make it 19LE24 or something like that. So customers free to do whatever slicing and dicing of the address space to make the load balancing actually work properly. And that's pretty much how it works there for between you and your customers. You go to the router D, the other aggregation router in the backbone, it has the same configuration. The only thing that's different is the point-to-point link. That's the only difference, the point-to-point link addresses. Everything else is the same configuration. Upstream ISP likes it because he's a standard configuration that he can put in a template, put in his provisioning system, and he doesn't have anything fancy or special to do. We'll look at router E. This connects elsewhere on the internet. So we prefix list customers out. We only let our customer aggregates out. We don't let the specific prefixes we've used for traffic engineering. So we strip the private AS because obviously 65534 is originating all these /19s. Strip the private AS, and then we have a prefix filter that only lets the /19 aggregates out. Now, if the customer prefixes came from the ISP's address block, don't announce them to internet. It doesn't provide any extra information. You simply announce the ISP's aggregate only. So you do something like this, prefix list my aggregate out, and then with the filter there. I've conveniently chosen the addresses to all aggregate into a /13. Okay, so that's generally what we try and do here. Unfortunately, if anybody's listened to my best practices BGP thing or any ranting about aggregation and so forth, not many people do this. Many people are just quite happy to leak all these sub-prefixes out with lame excuses like, ooh, well, if I don't do it, my customers don't get connectivity. Well, your customers get connectivity with this. Okay, /13 is just as routable as a /19. Okay, multi-homing to different ISPs. Well, here we need to use a public AS number. You can use a private AS number if you can agree with the other ISP. Sometimes two ISPs who are sharing a customer actually talk to each other. Sometimes it does actually happen. And so sometimes they can actually agree to use a private AS. When we were starting off in the UK, well, within a couple of years, we had a competitor in the form of the telco, British Telecom. They set up a competing ISP business with all the same services as we had and so forth. But you know, at the technical level, we got on pretty well with the technical folks there. And so we could do this type of thing. We could share an AS number for the customer and agree what multi-homing to do, which meant that the customer didn't have to go to the RIPE NCC to get an AS number. But that's pretty unusual. It's generally better to get an AS number for the customer, so you can get one, or the other ISP can get one, or they can actually get them as a one-off assignment. Again, it depends which RIR, but generally you can get a one-off assignment so the customer has their own AS number for this. You get an AS number for multi-homing, okay, between two different ASs. Okay, you get that. I mean, there's no discussion. There are 4 billion AS numbers, so it's not as though we're actually going to run out of them anytime soon. Address space being used for this comes from both upstreams. I find that a bit yucky. It's really hard to multi-home for reasons I said earlier, to multi-home between two different upstreams using their address space. It's much easier if you get your own address space for it. So generally for that, you can go to the Regional Internet Registry, either get a one-off assignment, or you can become an LIR and get your own allocation that way. So I'm not going to go into the situation of how you multi-home with two different upstream ISPs address space, because some places you basically can't do it. Some upstream ISPs simply do not allow you to announce their address space to anybody else. Or if you try and do it, they will disconnect you. So I'm not going to go down there. I'll go down the path of you have your own address block, this is what you do. Oh yes, the inconsistent AS thing. And there's always some discussion about inconsistent ASs. Some people seem to think this is bad, as though there's something illegal happening on the internet. I'm not quite sure why. I mean, there's nothing in the BGP spec that says this is bad. Inconsistent AS is quite often caused by this. You've got a private AS multi-homing between two ISPs or ASs, public ASs. So what you see in the internet routing table is a prefix that seems to be originated by AS210 and originated by AS200. It generally means that it's actually a private AS hiding in behind. They're originating the address block, announcing it to the two upstreams, who are stripping out the private AS and then announcing that prefix on into the internet. It's definitely not bad to do that. It's not illegal either, and I've seen people over the years say both things. They've never really explained why it is bad, apart from saying, well, because it just is. Well, that's not a reason. And illegal, it's like, okay, point me to the document that says you cannot do this. There's nothing in the BGP spec that says this is bad. In iOS, if you do show IP BGP inconsistent AS, you'll find all these. The last time I looked, it was, oh, it's a while since I've looked. It was about 600 prefixes all popped up like that. So it's not an insignificant number, but it's not exactly major beer either. So there's some out there. I mean, are they all doing this? I'm not so sure, but this is generally the case that you should see inconsistent ASs appearing. Sometimes they are genuine mistakes. Okay, two different ISPs. One link is primary, the other link is backup.
Just a comment. These, you mentioned that it's not illegal to advertise these smaller prefixes into the internet. It of course has the disadvantage that it increases the global routing table size.
For sure.
And then, yeah, I just want to mention that there's currently research going on in the research routing group within IRTF, and they are looking into approaches where you can actually avoid putting these small prefixes into the global routing table. One of the approaches is Lisp. And this is network-based. Basically, the functionalities in the provider ASs there, and then there is Shim6 and 6.1, which are host-based approaches.
Yep.
So they are trying to solve this.
Yep. Yep.
That's right. It's tomorrow.
And Scott is sitting right behind you. One of the Lispers. Yes, I mean there are other approaches being worked on. I think you know, a lot in all the cases it's still early work to try and figure out alternative ways. I mean, sidetrack. One of the whole big issues with multi-homing as it stands today is that it does not scale. Okay, what we've been doing at the moment, this is what we've been doing for the last, I don't know, donkey's years. And well, when the internet was small and so forth, it was all fine and good. At the moment, it is probably all fine and reasonably good, but there's a general scaling problem. The only way we have with trying to do any type of traffic engineering, I've kind of done the hint there of, well, you get your aggregate, to do load balancing, you're going to have to start subdividing your aggregate. A very, very common technique being used, which I don't like, but a common technique is, ooh, here's my address space. I've got my /16 from APNIC. Let me chop it up into 256/24s and spray out all the links I have and see what happens. This is very common. I see it happen an awful lot. And it seems to keep most ISPs quite happy. Sometimes they don't announce aggregates. Sometimes they do announce aggregates. Sometimes the networks fall over and don't work properly, so they put in some static routes until the links break. Until the links are fixed again, and then they take the static routes out. So we've got a dynamic routing protocol run by lots of people. So it's all really very ugly and messy and so forth. So yes, the basic issue is it does not scale. And of course, you know, with V6 being round the corner, as it's been for quite a while, V6 ain't going to scale either. Certainly not with the proliferation of proposals saying, ooh, we should give N sites /48s, or maybe we should give some people /64s, or maybe we should give some /56s. All these people who want that have never really explained how 2 to the power 64 /64s are going to work in the BGP table. So that makes the scaling problem an order of magnitude or many bigger. So hence the IRTF research, routing research working group efforts, or these people involved with that, trying to find ways of making multi-homing scale. So yes, there's talk on Lisp coming up in the NANOG session. It's going to be talked about at the RIPE meeting next week for anybody who's making the trek over to Europe. It has been talked about in various other fora as well as one of the examples of what's coming. I think once it actually appears on routers and is being used in the operational side, I'll come up here and talk about Lisp or whatever happens. But until then, I'll tell you what's working now. And what's working now is not good, but it's all that we have. So, 2 links to different ISPs. One is backup only. This actually does happen in real life, because you may have your main transit provider, and then you may get some backup through maybe a local competitor or something like that. In more developing parts of the internet seem to use this, so it has some kind of use. But what you do here is, you're sitting there, AS130, you'd announce your main /19 address block out to AS100, one upstream. You announce your address block out to the other upstream, AS120. But what you do here, you want this one to be the backup path, so you announce it with a longer AS path. Okay, so you sit out here on the internet. To get to AS130, you see a short AS path this way, and you see one that's slightly longer that way. The size of that AS path pre-pen determines, depends where you are on the internet and what the actual path link is from the internet center to where you're sitting. So one upstream provider may be a tier 1, global tier 1. Another upstream provider may be another local little ISP who's got 5 hops to get to a tier 1. so you have to do the prepends accordingly. Okay, so that's generally the case. So to make this the primary path for inbound traffic, we leave this alone. To make this the backup, we do a longer AS path prepend for our address space outbound to AS120. Okay, this is pretty much what I said. We always announce that in aggregate. That's really important. Both links always announce the aggregate. One link breaks, then because we announce the aggregate another link, we get the backup. Looking at the configuration, router A goes to AS100, so this is the primary path. Aggregate out, default route in. So just send a /19 out. We only need the upstream to send us a default route. Okay, that's all we're doing. We're only doing nearest exit routing at the moment. We're not doing any traffic engineering of outbound. That's coming up. So at the moment, we'll keep it simple. Default routes only from our upstream. Router B, again, aggregate out, default route in. So that's as we saw on router A. But we want to make this the backup path. So to do that, outbound, policy applied, router D out, which says set AS path prepend 130, 130, 130. What that does, it inserts 3 times AS130 in the AS path attribute. So when we get to AS130, it looks as though, sorry, AS120, AS130 is 4 AS hops away, rather than 1 AS hop away it would be by default. So it makes the path look longer. And then AS120 would announce this prefix to their upstream, and so on through the internet. And so you sit somewhere in the internet, you see 2 paths, one with a short AS path, and the other one with this 3 times AS130 AS path prepend. And that will, because this is a longer AS path, it becomes the backup. If we want this path to be the backup for outbound traffic as well, we then simply take the inbound default route we hear from our upstream and set local preference low. It makes it lower than the default of 100, so this becomes the backup. Okay, this was stolen again from working configurations. You just do the prepend for the outbound announcements to make that the backup for inbound traffic, and the default route you hear from your upstream, set a low local preference, lower than the default, and that becomes the backup for outbound. Okay, and that's quite straightforward. So it's not common because most organizations tend to want to use all the capacity that they have. But if you set up some situation where your 2 competing ISPs want to provide backup to each other, this one can be pretty useful. So let's look at load balancing in this situation. So we want to send some traffic on this link, some traffic on that link. Well, here we head off into the evil territory of announcing sub-prefixes. Unfortunately, there ain't no other way of doing this. So this is what we have to do. So we announce our /19 aggregate on both links, as usual. Okay, so aggregate this way, aggregate that way. And then to get load balancing or some kind of split of traffic between the 2 paths, say we chop the 19 into 2 pieces, we send the first /20 this way, the second /20 that way. Now this means all the traffic for the first /20 will come in this way. All the traffic for the second /20 will come in that way. Even traffic that goes from AS120 to the first /20, it'll go round like that. Traffic for the second /20 from AS100 will go round like this. Like the the smallest prefix size will always win. Right? A /20 will always override a /19. You can prepend the /20 as much as you want. It will always win over a /19. I mean, it amuses me. If you have a look at the internet routing table for long AS path prepends, you'll still find some ISPs who think that if they do a massive prepend on the /20, somehow the /19 will win. It won't. It can't. It can't ever. The /20 will always beat it. Okay? Oh, for sure. Yes. Yes. You negotiate with them. Yeah. Yeah. But you negotiate. I mean, a lot of ISPs, when they first set up the customer, it's like, oh, this is your address space. That's what I let in. So if you want to do load balancing, traffic engineering, you have to negotiate with them and say, okay, I want to leak some prefixes. And they may say, okay, we maybe let you subdivide by 2. Some may, we'll let you subdivide 4 times. So like /21. Others may say, oh, we don't care, remove prefix filter. Okay. Because they quite often don't. I mean, Yeah, I mean, no, for sure. No, but what you do, this is like the first cut. It's a bit like a binary search, right? So what you're going to do is you try this, see what happens. I mean, obviously, I would say in real life, this ain't going to work. So what you do is you maybe take the 19 and split it into 21s or 22s. And this is actually where addressing comes quite important in your address block as well. You know, when you're doing an addressing plan in ISP, people start numbering customers at this end and infrastructure at that end. Well, if you're trying to do load balancing and all your customers are here, well, they're going to generate all the traffic because your infrastructure is not going to generate any traffic at all. So if that's the case, then you've got to do your infrastructure here and then number your customers alternately from each end of the block so that you get some way of trying to do load balancing. Because otherwise you end up load balancing basically on /24s. And a lot of ISPs out there just say, this is too hard. So they just announce /24s and be done with it. And then something works. And that's a lot of what people are doing these days, which I'm trying to discourage because we've got 120,000 /24s in the BGP table at the moment. And a lot of them just don't need to be there. Okay. So yeah, so this is the first cut. As I say, it is just the first cut. It's basic inbound load sharing. Try this, see what happens. Of course, it's not going to work so well, so maybe take a 20, split it into two 21s. 121 on one way, on one link, and then this 20 and the 21 on the other link, and so on. Slice it until you get the load balancing you're after. Of course, what will happen then, you add the next customer, and suddenly it all doesn't work anymore. But so you've got to try and build some kind of sense into that. That's why I'm suggesting out of your address space, try and assign a customers from either end of the block, then you at least stand a chance of trying to do sensible load balancing. That's what I said all there. So this one, the configuration router A, so we generator aggregate as well as 1/prefix. We let them out to the upstream. That's all fine. Router B, we do the other /20 and the aggregate, let that out to the upstream. So that's all fine. So it is a basic concept. Let's try another way of doing load sharing. This is just another way of trying to do this. This might work a little bit better. I prefer this over the previous one. So this one here, I announced just the 19 on one link. I announced the 19 on the other link, but with a prepend, ASPath prepend, to make it look further away. And then I leak 1/20 subprefix. Okay. What happens here is all the traffic for this /20 will always come in this path. And then the rest of the traffic will just fall, well, as the cookie crumbles or whatever. So some might come in this way, some might come in that way. So I prefer this one a little bit better because you've got the /20. You can change the size of that. You can make it a 21, maybe a couple of 22s in different parts of the 19. It's a bit like a slider or volume control. You can just change that size as you wish. So any ISP I go and help with trying to do load balancing like this, we go down this path. 19 out one link, 19 with an ASPath prepend out the other link, and then leak one subprefix. And that's generally all you need. When I've converted ISPs who've got, say, a /19, they're announcing out 32 /24s. I've converted them from announcing 33 prefixes to announcing 2. And they've got exactly the same functionality. Exactly the same. Because we've gone down this path, aggregate this way, aggregate that way with a prepend, and then one single subprefix. Okay? It doesn't have to be a /20. But you start with a 20 and see what happens. If it's too much, then, well, reduce it. Make it a 21. Find out the busy address space in your network. So use something like NetFlow. Find out the popular local customer activity. You know, if somebody's always downloading DVDs and so forth, then, well, it's going to probably cause a bit of challenge, but you want to try and funnel them a particular way. The other situation where you see this used is you've got special customers. Right? You've got special customers that to pay you an awful lot of money for really good internet connection. Right, you number them out of a particular address block. You leak that address block out through your special upstream who's very, very nice to you. And then everybody else, you just let them wander in through this one who's not so good. And if this link gets wedged, who cares? Okay? As long as your really special customers get as much bandwidth as they need through the alternative path. So again, that's another type of traffic engineering load balancing thing that people quite commonly use. Okay, so this is what I talked about. Configurations are there. So Link to AS100, default in, aggregate out, that's all simple. Router B going to the other one, so we send the aggregate out, and also one sub prefix out, so whereas it subblocks out, basically allows the 19, okay, and the sub prefix /20 as well. And the route map here applies our policy, and it says if the prefix is an aggregate, we do a 2 times prepend. This is the other volume control thing that you have. You can change the size of the prepend. Okay? You can make it a single prepend, 2 times prepend, 3 times prepend. It depends on the topology between you and your upstreams to the center of the internet. I tend to measure the center of the internet by coming to somewhere here in the US, or maybe going to parts of Europe and doing traces or looking at AS paths back to where the ISPs are. So if you're sitting here, it's probably pretty easy. But other parts of the world, if you're helping customers there, they probably should start from somewhere here, going back to them. So the other thing you can vary is the AS path prepend here. And that just varies where the best path decision is being made, which AS, how many AS hops away. So maybe 2 AS hops away with a 2 times prepend. It could be 3 AS hops away with a 3 times prepend. Okay, it just depends on your topology. So those are the 2 things you can vary, the size of sub-prefix you're leaking and the amount of AS path prepend you push on the aggregate. Okay, and this is my favorite way of trying to do the load balancing. I find it quite common as well. If I look in quite a few ISPs, quite a few of them are doing this type of thing, massaging the prepend and the size of sub-prefix they're leaking. And this works pretty well. Okay, let's move on to load balancing outbound traffic, which is really what the next traffic engineering thing is all about. Okay, all these people who do MPLS stole the name traffic engineering. We were doing traffic engineering BGP a long time before MPLS came along. So I've called this bit traffic engineering. It's trying to really balance inbound and outbound traffic flows. So we've seen how to balance inbound traffic flows. It's how you announce the prefixes out. That's generally pretty easy to do because you control the address space that you're announcing. Okay? What you announce determines what comes into the network. So you can do that. But it's balancing outbound traffic that's a little bit more entertaining to try and do. You want to try and balance link utilization. Quite a few people want to do that, certainly for transit ISPs. Some people want to try and keep traffic flows symmetric. Again, it may not matter so much within, say, a geography like North America, but if you're sitting in parts of the world, say Africa or Middle East, South Asia, you've got satellite connections, or you've got very, very expensive international links that, say, one circuit goes to North America, another one lands in Northeast Asia somewhere. You want to try and be as symmetrical as possible. You're trying to get to European sites. You don't particularly want your packets to go out to the European connection, but come back in through the Asian connection, because then your packets end up going all the way around the globe, which just gives you longer round trip times and a less happy experience. So the desire to make traffic flows symmetric is there as well. Okay, so balancing outbound traffic requires inbound routing information. So the common solution is, hey guys, you need the full internet routing table. And again, because I'm spending a lot of time in developing parts of the internet, I see those emails quite often coming from the major upstream providers. Little ISP wants to multi-home because they understand the redundancy and reliability story, and so they want to multi-home. And they've got the 15-year-old Cisco 2501, and they want to go and multi-home. So they speak to their upstream, and the upstream says, yep, you need a whatever, massive piece of iron. Because, yep, you need a full routing table. Minimum we support is this model number of this particular router. And these guys come back to me and say, yeah, they're saying we need to buy this. We can't afford that. This is the annual gross domestic product of our country or something. Can you make it work with my 2501? It's like, yep, sure, no problem at all. Send these emails. So all I do is send emails which say all the yes, say that. So it's, okay, email to upstream 1, send me this. Upstream 2, send me that. And the upstreams are quite happy because then think, oh, the ISP's got the right router. And if it's a Cisco box, then I suppress the CDP so the upstream can't find out what's actually running. And then we can make it work on our 15-year-old box just fine. Common solution, full internet routing table. It's rarely necessary, actually. You can do an amazing amount of thing with default routes. So as I say, keep it simple. It's a lot easier and often much, much cheaper than trying to carry n copies of the full table. So 3 myths I'll just wander through. The first one, you need the full routing table to multi-home. Well, people who sell router memory would like you to believe this. I mean, you need 256 meg of RAM on a Cisco box these days to get the full table. I don't think you can squeeze it into 128 anymore, and I think you probably can just squeeze it in to 192 with a few left. Just don't go here. You need a big amount of memory. It's only really true if you're a transit provider. And you're a transit provider, you're going to use big boxes which come with 2 gigs of RAM anyway. So a full table can actually be a significant hindrance to multi-homing. You need a big router to multi-home. Well, router sizes are all to do about throughput. You know, big routers tend to have optical connections and OC 192s and all these type of interfaces. To multi-home, you need to actually run BGP. You can run BGP in a router that's got 2 interfaces. Okay, so any little thing with sufficient interfaces, sufficient memory, like 4 meg or something, that will run BGP just fine. Right, so you need 2 interfaces, be able to talk BGP to at least 2 peers, and be able to handle BGP attributes and handle at least 1 prefix. Works fine. Yeah. Yeah. Works fine. Yeah. I mean, and the CLI looks like iOS as well, so pretty much if you've seen that before, you can just dump it on there and go for it. Yeah. I mean, pretty much anything that handles BGP. I mean, there's OpenBGPD guys for, what's that, OpenBSD? That one works fine too. And again, it's a very Cisco-like CLI. It's pretty much anything that handles BGP. And you find, you know, many parts of the world, people just don't want to go and buy the green or blue box. They go and get the crappy old PC from somewhere that can run, I don't know, Red Hat 9 or something suitably ancient and put Quagga on it, and it's just fine. I mean, the example I talked about, 2501, I'm not joking. I'm not making that up. That's real. Okay, it works perfectly well because that thing, it'll take two 2 meg connections quite happily, and even though it's still a Motorola 6830, I think it is, CPU, works just fine. Okay, and that's the thing. There's not much needed really to run BGP at all. It's not the size of the thing. So your salespeople coming along to try and sell you big boxes, yeah, as I said at the start, don't get your sales guys to sell you, your vendor sales guys to try and design your network for you. Sure, they'll design you a very, very nice network. Is it just the one that you want? That's the thing to be aware of. Final one, BGP is complex. Remember my Mongolia story. In the wrong hands, it can be. BGP is not complex. BGP is actually very, very simple. You can make it very, very complex if you try. It's very, very easy to make it very, very complex. Yes, you can be overawed by any of the Tier 1 ISP's BGP configurations as they show you screens and screens and screens of some very, very, very complicated stuff. Okay, when you learn to drive a car, did you learn to drive a car by entering any of the big motor races? No, you did not. You were probably put, well, like where I grew up in a farm, so I learned to drive a car in a field. And it was a big field, so when I didn't run into anything at the side. Okay, it's the same type of thing with learning this stuff. Keep it nice and simple. Don't get carried away. Don't get complex. Take some of the examples I've got here. Play on a spare router. Get something like Quagga on a PC. Go play with it there. Get the feeling for how things are. Right, here's some strategies. Take the prefixes you need to aid traffic engineering. Right, it's not just a case of throw stuff up in the air. Oh, 230,000 prefixes, what on earth to do with them? Look at NetFlow. Yes, I am not joking. Look at NetFlow. I mean, NetFlow is probably all the things that people love in the security arena. Right? It tells you all what's happening in your network and so forth. And when I do these tutorials in other parts of the world and I say, look at NetFlow. How many people use NetFlow? And people go, huh? What's NetFlow? What? I mean, you haven't switched this on your router? It's only been available for about the last 10, 11 years now? And it tells you valuable information about the traffic flows running through your router. Put this on the edge of your network. You know where your customers are going to. You know who's looking into your network to do stuff. You know where the popular destinations are. Export the flows, aggregate them all. You get lots of useful information. Generally, prefixes originated by your immediate neighbors and their neighbors will do an awful lot more to aid with load balancing than prefixes from many ASNs away. We're sitting here in the US. Who cares what's happening in, well, I don't know, Mongolia, for example. Right? It's not going to make any difference for your traffic engineering, so why bother with having any of those prefixes? A default route will usually work just fine. So as I say, use default routing as much as possible and use the full table with care. So I'm going to look at these 4 examples. Hopefully I can fit all those in when am I meant to finish? 5 o'clock, I think. So we'll look at those examples in the time I've got left. So hopefully it'll all fit. So each example assumes we've got a /19 address block. It'll work with any size of address space, but I'm just going to use that in the examples. We've got one upstream, one local peer. Okay, so you connect to your transit provider, and then you do some local peering just because, well, it seems a bit silly to send traffic halfway around the country if it's only really meant to go down the street via your competitor. So what are we looking at? So we're here, AS110. We've got one router connecting to our local peer. We've got another router connecting to our upstream. Notice 2 routers. If I just had one, then I'd have a problem. If the router broke, I'd lose all my connections. Where at least here, if one router breaks, I still have connectivity to either my local peer or to my upstream. Okay, so that's still a better situation. So any type of multi-homing, really try and use 2 different routers. So what we're doing, we announce the 19 aggregate on each link, accept the default route only from the upstream. That's all you need. Right? Upstream can send you the full BGP feed. It buys you nothing at all apart from 234,000 prefix headache. And from the local peer, accept all the prefixes that they originate. Right? Just accept the prefixes they originate. If they accidentally send you the default route, well, this might be a bad thing. Well, it should be a bad thing, but, well, some people take advantage of that as well, which I probably wouldn't really recommend. Generally accept any prefixes originated by their AS. That's what you want to do. So looking at router A, so we're originating our /19. Outbound, we send our prefix list out to the local peer. Inbound, we accept just the prefixes they originate. So I've done a prefix filter. That's the best way of filtering anything a peer would send you. Do it per prefix. Again, you'll be amazed how many ISPs simply have nothing set up there at all. Or they may have a prefix filter that just throws away private address space or something. They accept everything the local peer sends them. They trust the local peer to do the filtering for them. I mean, would you trust a competitor to run your network for you? I don't think so. Some people use AS path filters. So rather than using a prefix filter, they use an AS path filter for the inbound announcements. Right? So this says anything originated by AS120, or if the AS120 does an AS path prepend, we're going to accept it. So that assumes that AS120 knows what they're doing, and they're not going to originate junk into your network. All right? So that's one to watch as well. Should you do this? Well, what we actually did at UUNet, we had the prefix filter, and then we backed it up with an AS path filter. So if we blew away the prefix filter for any reason, at least the AS path filter gave us some kind of security. All right? I wouldn't really do the AS path filter by itself unless you really, really trust the guy who's running the other network. I mean, if he's your best friend, then it's probably okay. And if the CEOs of your 2 companies are best friends as well, that's probably okay as well. Because if he makes a mistake, you don't want the CEOs to fall out with you or something. But so generally, as I say here, AS path filters are a lot more trusting. The router C configuration, well, this is connecting to your upstream. Very simple, default route in, my address block out, that is it. Okay. The only configuration I don't have here is the IBGP between router A and router C. That's the only thing I've missed out. All right. This is just real working configurations that do actually work. I mean, I've dropped these into so many different networks in the last few years, and it just works. And people go, wow, is that all I have to do? Yes, BGP is really complicated, isn't it? Not. Okay, so 2 configurations possible for router A. The prefix list is higher maintenance because every time your local peer adds a new prefix, you've got to update your filters. But that's what good ISPs should be doing, right? If this new prefix is going to be announced, you update your filters. So in some parts of the world, people use internet routing registries, so they update the internet routing registry, and so filters are automatically built from that and automatically updated. Other people use email. Other people, well, the bad ones just don't bother doing anything at all. The filter list assumes the peer knows what they're doing. Well, if you want to go down that path, the caveats I've already mentioned. There's some configuration recommendations just to be aware of. A private peer is just that. What you're doing is you're exchanging prefixes that you originate. Okay? That's quite important. You don't really want to have the full BGP table on a private peering router. If you've got that, then your private peer could point a static default route to you and use you for outbound transit. And if he's a content provider, he would love to do that, because it means he doesn't have a very, very big fat pipe for his outbound traffic. He can send it all through you. Be aware, this does happen a lot. Okay, it's not an unusual thing that I just happened to mention because it could happen. This happens a lot. Yes, you could put packet filters on the interface. Packet filters tend to be a little bit more expensive on the router than doing this. It's much easier just not to carry a default route or the full BGP table on that router. Okay, much, much easier than putting packet filters on the interface. What about the next example? Well, one upstream, the local internet exchange point. So this is the natural progression of the previous example. You've got lots of local peers. They're all at an internet exchange point. What do we do here? Well, it's the same deal, really. You've got the router A here, peering with all these other ISPs at the internet exchange point, and you've got router C going to your upstream. Okay, so we're announcing /19 aggregate to every neighboring AS. As before, we always announce our aggregate. We accept only the default route from the upstream. We do not need the full BGP table. It's not giving us any extra information. The local exchange point peers are going to announce the prefixes they originate towards us. And we're going to announce our prefix towards the exchange point peers. So all the local traffic stays local across the exchange point. So we look at router A. So I've gone a bit overboard with the configuration here. So there's the fast Ethernet interface connecting with the exchange point LAN. I've done the reverse path forwarding check just for fun. And then I've got the BGP configuration. I can use a peer group because all the configuration for each peer is exactly the same. Right, each peer is going to hear my address block. Each peer we're going to remove any private ASs in my network. And we're going to use a route map to set high local preference. Basically, I want to prefer any traffic to my local peers going across the exchange point. I have ended up with situations at some exchange points where the best path has still been through the upstream for various reasons. You don't want that. You want the best path to the local peer to be across the exchange point, so setting a high local preference makes absolutely sure that that happens, and it also makes sure that the RPF check actually works without creating a black hole in the network. And then the rest of the configuration, we just apply the peer group to each neighbor. Notice we still have separate inbound filters for each of the exchange point peers. Right, this generally shouldn't be too much maintenance to do once you've got it set up. As I say, you find that quite a few exchange points tend to make use of the Internet Routing Registry these days. Each ISP puts the routing policy in the registry, and then everybody can build their filters from that policy. You can use something like the IRR toolset to build your filters, and the IRR toolset supports Cisco and Juniper and Foundry and quite a few others as well. So there's really not much reason for not doing that. If you look at, say, for example, the best ones I know are the New Zealand Internet Exchanges. They all use the Internet Routing Registry at the exchange point for building all their filters. And it's, if you're on the NZNOG mailing list, then you see the announcements every few days. Somebody's added a new address space announcement, so you get the NZNOG mailing list coming from the registry saying, hey, registry's been updated, please update your filters. And people have automated a lot of the filter construction, so it all gets automatically done pretty quickly. Okay, the final slide, they're the prefix lists for the filters for each of the local peers. And then I've set the high local preference for anything I've heard across the exchange point. Okay, note that router A does not generate the aggregate for AS110. Now, router A, remember, if we go back, router A was this router here, connecting to the exchange point. He does not generate the aggregate. Quite often, this router is remote from your backbone. It's connected by a single connection from your network to the exchange point. What you don't want to happen is your router A gets chopped off from your backbone. It's still announcing the aggregate to the exchange point, and then everybody here says, oh, best path to router A is this way across the exchange point fabric. What you want to happen if your router A gets disconnected from your backbone is that you get backup through your upstream and through their upstreams, and you want that to work. Whereas if you generate the aggregate here, well, sure, outbound traffic will still go this way. It gets to this router here or this network here, and he says, best path is through the exchange point. Drops onto router A. Router A has a static route to the null interface or the discard interface. Boom, everything gone. You end up cutting yourself off from your local peers. Right, so it's really important not to generate the aggregate on the exchange point router. That again is just another best practice tip from years of misexperience. Okay, so then the BGP failover will work as expected. Note the inbound route map, which sets the high local preference and avoids problems with the URPF check. Router C configuration, no surprises here. We accept the default from the upstream. We send our aggregate out to the upstream. Again, it's a very simple configuration. Prefix list, high maintenance, but it's generally safer to do, the URPF, and so forth. So this is all working fine. Again, if you're at an exchange point, do you want to ask? Any thoughts on setting max prefix, just for the benefit of the video? I would probably generally set max prefix, but so the thing is with max prefix, you've got two options. You can set it to tear down the session, which you probably, well, maybe you want, maybe you don't want, it depends on the scenario. You can also set it to do warning only. So if your NOC or your management system actually pays attention to the max prefix warnings, then it'll page you as soon as it hits the threshold, so you can go and fix something pretty quickly. So I think, yes, using max prefix would be a good idea, but maybe only in the warning only mode, so it doesn't tear the session down. Not necessarily, because it could just be like they end up sending you one extra prefix, 0.0.0.0/0, and then you're blown out of the water because you give local pref 150 to that, and that becomes your default route out of your backbone. Yeah, and then you're adding extra bits and pieces, which is yeah. And that's it. I mean, there's several ways of trying to do this, and I mean, I've just presented really what I've tried to do with the exchange points I've been involved in. Again, just to try and avoid complexity. It's like, look, guys, only filter what you expect to get from these people. Then there are no surprises, less chances of mistakes, less chances of bits of configuration getting blown away. I think once you've got experience with doing this, then you can look at something a bit more sophisticated, like I was talking about. But certainly if you look at some of the exchanges I've seen, some of the ones that are a bit more developed, they make heavy use of the Internet Routing Registry and try and insist that the members use it, build the configurations from that. So you get quite specific configs from that. But it's the usual thing, whatever works best for you. This is again just from my experience of working with the various IXPs. Be aware that the exchange point border routers should carry only the prefixes you want the exchange point peers to receive and the destinations you want them to reach. Otherwise, they could point a default route to you and unintentionally transit your backbone. Yes, you can put packet filters in to try and stop this, but packet filters tend to take a lot more overhead than just a simple, well, only carry your IBGP. And if the exchange point router is at the IX and it's distant from your backbone, don't originate the address block at your IXP router. Otherwise, you end up causing yourself a little black hole problem. Okay, now let's look at 2 upstreams and 1 local peer. So this is a bit more content to try and think about. So here you're going to connect to 2 upstream transit providers to see the internet. And this will give you external redundancy and diversity, and this is really the reason for you to multi-home. And of course, you have any other local peering, we kind of ignore that because we know how to handle it. So router C and router D are connecting to 2 different upstreams. Notice I've separated router C and D. If you merge C and D, you end up with 2 connections to your upstreams on the same box. The box falls over, you lose both upstreams. So what we're doing, we're announcing /19 aggregate on each link, as usual. Without that, we don't get backup if 1 link fails. We accept the default route only from our upstreams. This is the first cut. I'm going to show you why this doesn't really work so well. Accept the default route only from the upstreams, accept all routes from local peer, the ones that they originate, and that's done. So router C, we accept the default, we send aggregate out. Router D, we accept the default, we send aggregate out. Problems with this? Well, there's some problems. The outbound traffic will only take nearest exit, which is really not very good for what we're trying to do. I mean, we don't need any fancy routers because we only got the default route, which is like one prefix. And especially if you've got big links, big external links going to different places, different parts of the planet, then it's really not very useful at all because you can end up with some really wackily asymmetric routing. So the load sharing for this needs to be a lot better. And there are two better options, or there are two options to consider. The first one is to accept full routing from both upstreams. 234,000 prefixes times 2. So you end up with 468,000 paths in your BGP table. Okay, throw some memory at it. You know, Cisco and Juniper will sell you some lovely memory, and it won't be a problem for you. But 468,000 paths. What have you got? 3 upstreams. Add another 234 to that. 4 upstreams, 5 upstreams. It starts getting a huge amount of real estate to try and handle. Okay, so that's one option. Another option is to accept the default route from one upstream and some prefixes from another upstream. And that's actually the preferred way to go. I mean, the main issue is you end up with a huge amount of prefixes less to carry. Default route is 1. Few prefixes could be anything like 30, 40,000. So you end up playing with 30,000 prefixes to try and do your outbound load balancing rather than with 468,000. That makes a big difference, especially when it comes to convergence speeds. So, pardon me, let's look at this one. So for full routes, well, what we do is we've got an inbound filter which says accept everything apart from RFC 1918 and friends. So that would be the Team Cymru inbound filter, for example. So private addresses and your own address space, 169.254, various other non-routable addresses that are documented in RFC 3330. We've got this route map here called AS130 load share. It's not a built-in Cisco thing. It's something that you actually have to go and configure up. And that's on the next slide. What this is doing is it's saying any prefixes that come from AS130 or the immediate AS neighbor of AS130, we're going to set a high local preference. What that's saying is the best path outbound to AS130 and AS130's neighbors are out through AS130. Because you're going to say, well, okay, AS130 is close to me and their neighbors are close to me. I don't want to go through my other upstream to get to AS130's neighbors. I want to go through AS130 to get to them and their neighbors. So setting the high local preference makes absolutely sure that this will happen. And then you say for everybody else, I set them a low local preference, so I make it 80. This is the full BGP feed. So all the traffic that goes to 130 and their neighbors goes out this way. Everything else does not go out this way because we've made the local preference low. And on router D, basically we do the same inbound filter, accept the full BGP feed, block all the ones we're not supposed to hear. And that's it. Okay? So what do we have on the router? Or what do we have in our iBGP? Well, we've heard 234,000 prefixes from router C and their upstream. We've heard 234,000 prefixes from router D's upstream. On router C, we've, say, maybe 30,000 prefixes got local pref 120. 214,000 prefixes got local pref 80. And then we've got 234,000 prefixes of local pref 100. Wow, isn't that an exciting time? So the router's got to do best path selection through 468,000 paths. And we'll put 234,000 entries in the fib. And of course, this all happens at the speed of light, and it happens in 1 microsecond. Well, not really. It actually takes quite a bit longer to do that. And even with the biggest, fastest route processing engines and the biggest routers today, it still can take a few minutes to actually become reality to do this. So that's a few minutes convergence time, which is probably less than wonderful. Okay, so that's really what I've just been saying. It's expensive. You need memory to do this for the 468,000 paths. And CPU. You need a really big, brawny CPU to try and process all the best paths for those as quickly as possible. And you need to play a lot of local preference games. You need to set local preference on a whole heap of prefix on one peering. Okay. Now this is an example, but anybody who's trying to multi-home with two upstreams like this tends to go some way down this particular path. I've kind of exaggerated, but this is typically where you can end up in certainly a poorer case scenario. Actually, the better strategy is to use partial routes. So what to do is ask one upstream for a default. Okay, so just get one upstream to send your default route. So all they need to do is a default originate on their BGP session, and that's it. They send your default route. Ask the other upstream for a full BGP table. Right? And then you filter this table based on the neighboring ASN. So what you do is ask them for the full table and throw most of it away. You can't really go to your upstream ISP and say, oh, I want this prefix and that prefix, but I don't want this one, I don't want that one. Or maybe give me a bit of this and not a bit of that. Okay? You're not going to get any upstream provider to play that game with 234,000 prefixes. Right? They're not going to do it. They'll either give you the full table or the default. Some people give you something in between, but some people give you the IBGP prefixes, which I kind of don't quite understand. If somebody can tell me why that makes sense, please do. Because I have no idea why this makes any sense whatsoever, but it seems to be rife through South Asia especially. Yeah, why is that useful? Yeah, but why not just send an aggregate? I mean, customer rights I can understand, but I would like to see it as an aggregate rather than 30,000 /28s and 29s and 30s. If you jump onto an ISP who connects to, say, VSNL or Bharti or Reliance, you'll see what I mean. It's scary. And I've worked for a few ISPs or customers of them, and the BGP from these guys, it's 30,000 prefixes of 29s and 28s and so forth. It's like, why are you sending me this stuff? Send me an aggregate. Oh, no, we can't send aggregates. Why not? Anyway, I'm not going down that conversation, but, it's that common thing. Sending customer prefixes as an aggregate, I understand, but sending all the little bits and pieces, I don't want to see your /30s that you use for all the point-to-point links that you're NOx monitoring. Why do I care? How is it going to make any difference? They all should be part of a covering aggregate. But generally from your upstream, you see the full table or just the default route. So that's what you have to play with. And so you can then go and customize your filters. So router C, well, here we're going to basically take, what are we going to do here? We're going to take the full BGP feed and, basically throw away everything apart from, not throw away. We're going to accept everything apart from the private addresses. Then we've got outbound prefix filter, which says only let my address block out. We've got a filter list. Now this filter list 10 is an AS path filter. And that one says accept all prefixes originated by AS130 and AS130's neighbors. So it's the same one as we had in the previous example, but rather than setting local preference, it's just what we accept. And then we've got a route map here. So if we get the default route from this upstream provider as well, we tag it low, so we make it the backup. All right. So there's the rest of the configuration. Tag default low. If they send us the default route, we set the local preference to 80, and everything else we leave alone. And here's the AS path filter. It says anything from 130 and their neighbors, we're going to accept inbound, and we discard everything else. So even though the upstream has sent us 234,000 prefixes, we probably only end up with a default route and the 30,000 from them and the neighbors. 30,000 is just an example number. I don't know who it is. It depends on who your upstream would be. But it's just by way of example here. So we've ended up with 30,000 prefixes from this peering. This peering, default in, aggregate out. So we've ended up with 30,001 prefixes. Okay, best path selection here. Well, we've only got one best path selection to do. Which default route do we use? Okay, so this really does take a microsecond for the router to converge. Okay, so we're dealing 30,001 prefixes here, 30,000 fib entries, 30,001 paths. Very, very easy to do. You can do this on a really small router, no problems whatsoever. So you see why that a lot of the ISPs who can't buy the big real estate from the vendors, they're using the smaller, older routers, they all barrel off down this particular path. This is what they do. It's the only thing that they can do. Default route from one, and then accept full feed from the other one and discard most of it, because it's much cheaper for them to actually do. What about IGP? Well, you can pop the default route into your OSPF. Again, it converges much faster than the IBGP default route. So pop it into OSPF. So this becomes the backup. Metric 30 is not as important as metric 10. As long as the default route's heard by BGP, in other words, the default route's in the routing table, OSPF will put it in the OSPF version of the routing table. And so a default will be distributed by OSPF. So if one link goes down, the default disappears, and then OSPF will withdraw the default route, and so the other default becomes chosen. So again, this is stolen off from current working ISP. They get very, very fast convergence if one link drops. If one link drops, basically the default route disappears, and they flip over at the rate of OSPF convergence to the other transit provider. So it's actually really, really quick. Compared with what they were doing before, which was 2 full BGP feeds, and would take them about anywhere between 10 and 15 minutes to fail over if a link broke. So they're pretty happy with this solution, as you can imagine, because it's almost instant. Okay, so I've talked about all this. So this is a lot cheaper to do than the full table. You've got much fewer prefixes to handle. Obviously needs fine-tuning. The next example is going to show you some fine-tuning. Oh, by the way, if you're going to distribute the internal default by IBGP or OSPF, any router that's on a private peering, whether it's private, or at an exchange point, don't have a default route there. So the simple thing to do, point a static route for the default to the null interface, or discard interface if you're on a Juniper box. Okay, and that way, the default route, this static route will override anything learned by IGP or BGP because the distance of this is 1, so very important, compared with distance 110 for OSPF or 200 for IBGP. So that's just another tip to be aware of. Now, this one's a bit more interesting. We've got 3 upstreams, 3 unequal bandwidths. This is just a kind of strategy to show, I won't spend too long on it, but it shows you the kind of thinking how to try and do load balancing for this particular situation. The bandwidths are all scalable. It depends where the ISPs are and all this type of thing. Say, for example, we've got 8 meg to ISP A, 4 meg to ISP B, and 2 meg to ISP C. Well, one option here is the full table. 700,000 paths today. We can do that, no problems at all. I'm happy to sell you a big router with my router vendor hat on. I can sell you lots of big routers for your backbone with loads and loads of memory in them. And the salespeople are all happy because they get big commission and all the rest. The other thing we can do is try and make the service provider happy. So the other option is to make him happy is to use partial table and try and use as many defaults as possible. So this is a strategy that I see quite a few people use, and it's a strategy that I use as well. You don't need to have 3 routers for the external peerings. 2 is fine. You put the biggest connection, which is to ISPA, on one router, and then the 2 smaller ones on the other router. So if this link breaks, you've got 8 meg there, you've got 6 meg joined together here. So if this one breaks, then you've got some chance of pushing some of the traffic onto those 2 paths. Likewise, if these 2 break, you can push some of the traffic onto that path. Okay? So what do we do? Well, the transit provider will be happy to give you a full table, and he'll give customer prefixes and default, or he'll give just the default. That's all. It's tick box. I've seen the form coming from this particular ISP. Quite seriously. BGP required? Yes, no. If yes, tick which box you want. And that's how it came through in the... So I didn't know whether to be impressed or not, but I was impressed, so I ticked the box for... Which one was this? I don't remember now. Anyway, I think it was the ISPA example. I ticked the box for default route, please. Okay? It's very rare for any upstream to offer anything different. Right. So accept only the default route from provider with the largest connectivity. By definition, the largest connectivity will have most of the traffic. Most of the traffic is hopefully generated by most of the prefixes. That's kind of naive, but it seems to actually work by and large. If ISPA won't give the default, still run BGP with them, but discard everything. So you run BGP so you can announce your aggregate to them. They send you 0 prefixes. You just use the OSPF trick I was talking about. So set up a static route pointing to this upstream, and then you do the default information originate into OSPF, so OSPF distributes a default route. Request the full table from B and C. Yes, it sounds a little bit illogical to get the full table from the providers who've got the smallest links. But what you're going to do is you're going to throw away most of the prefixes you hear from B and C. Okay, you're going to throw away most of those prefixes. Default plus customers is rarely enough in this particular situation. This is why I'm always mystified why it's given to me. So how do you decide what to keep and what to discard from ISPs B and C? Well, most traffic is going to use the ISP A link. So what we need to do is try and find something that's closest to B and C. So that's my strategy. ISP B is going to have customers as well, like me. So I want to reach customers of ISP B and C through B and C. I don't want to reach them through A, because that invariably means going round a long path. So I want to go through B and C. So I'm going to keep those prefixes. So anything that B and C sends me, I'm going to keep anything they originate for the statically connected customers and any neighboring ASs for their BGP customers. Okay. I'm going to discard prefixes transiting the global transit ISPs. Okay, global transit ISPs generally appear in most non-local or regional AS paths. Right, so those are like your, I don't know, big tier ones, whoever they are. I'm going to discard those because they're going to see most of the traffic I'm going to see anyway, and most of those are going to come through the router A or ISP A link. I'm going to see them from my biggest pipe. Discard prefixes with ISP's A ASN in the path. You're going to see ISP A's ASN through ISP A link. So there's no need to see them through ISP B or ISP C. Default will do fine there. Right, so you don't want to see those through, so you can throw those away as well. So the global transit ISPs, well, I don't know if these really are them or not. There are probably others. Depends on marketing departments more than anything. But what a colleague of mine, if you remember, well, a colleague of mine at NANOG, you know of Gara Bupadia working for PCH. Some research work he was doing to try and find badness in the AS paths on the internet. He discovered that these 4 ASs never ever appear more than 2 in the path. You never ever see more than 2 of these ASs in any AS path on the internet. And given that the global transit ISPs don't pay each other for transit, this seems probably a reasonable assumption. I'm probably wrong, there's probably somebody else in there, but I'm using this as my assumption. So if there's anybody else in there who thinks this should be there, don't shoot me. So I'm discarding basically any prefix with these guys in the path, because I'm going to hear anything that's gone through those guys on my biggest, fattest pipe. Okay? I'm also this is on the ISP B peering. I'm also going to discard any prefixes with ISP A's AS path in the path, because I'm going to hear all traffic from them coming through the ISP A link. Likewise, ISP C, I'm going to hear them through the ISP C link, so I don't want to see those AS paths. So what I'm left with is basically prefixes that are directly reachable via ISP-B. So anything they originate, what the neighbors originate, and then I've added in 2 more for good measure. This is something I stole from an ISP that I helped set up their peering with in Nepal. So this kind of worked for them. We threw away all these, we threw away their 2 other transit providers, and then everything from their upstream, the upstream's neighbors, their neighbors, and their neighbors. And that gave them, funnily enough, round about 25,000 prefixes. Okay? So that worked. That worked kind of pretty well. Okay, so that's explaining what I've done. Permitting prefixes from ISP-B and their BGP neighbors and their neighbors and their neighbors. If you get not enough traffic on the link, allow some more prefixes in by just adding a bit more to, just adding another line to the AS path access list there. If there are too many prefixes, therefore too much traffic going out, then maybe drop 1 line here. This is quite tunable. Okay? If you can't get this right, maybe consider dropping one of these. Okay, there's lots of things you can actually tune to try and make this work well. Okay? A similar filter can be built for the ISP-C BGP peering. I know it looks a little bit complex, but the same thing can be built for ISP-C. The same prefixes are heard from both B and C, then establish a proximity of the origin ASN to B or C. You find that maybe some European ISPs have got 1 point of presence in Asia. And in this case it was BT Ignite. Right, BT Ignite is by and large within Europe. But they'll probably have a POP here in North America, and they do have a POP in Japan. So you sometimes see best path from, say, South Asia to London is through Japan, through BT Ignite, even though it doesn't make any sense because the best path is actually on the direct link. So you've got to kind of watch that the AS path length doesn't necessarily refer to what's the best geographical path or the best RTT. So you have to build in allowances for that as well. Okay, so this is that particular example. So transiting to particular ASNs via particular ISPs may make more sense. So you can include those in your filters as well. Okay, so that's my strategy, my inbound load balancing strategy. The largest outbound link should announce just the aggregate. Other links can announce the aggregate with an AS path prepend. Maybe the ISPB link can announce a single prepend. ISPC link announce double prepend. You could maybe announce sub-prefixes as well. So the biggest, fattest pipe can just announce the aggregate. Maybe the link to ISPB is handling just broadband customers. You don't want to give broadband customers unlimited access to all your external connection. So once they've filled up the ISPB link, too bad. They can complain, well, because they only pay $10 a month anyway. So just once they're full up, end of story. ISPC link could be used for commercial lease line customers you want to be very, very nice to. Okay, so you make sure that it's always ever running at 50% capacity and nobody else from your backbone can use it. And so many people get tied up in knots about QoS commands on routers and rate limiting and rate limiters and traffic shapers and buying big expensive boxes. You can do a lot of stuff with BGP just by careful announcements that you make out onto the network. And I mean, I made these guys traffic shaper completely obsolete just by doing all this. And they were like, how do you manage to do that with BGP? Because they were using some fancy traffic shaping box after the BGP routers to get all the traffic for different customers sorted out right. So this all worked pretty well. So the eBGP configuration example for router A. So this is the biggest pipe. Default router in, aggregate out. That was very, very simple. The router B configuration, we're going to ISPB. There's a filter list 1 in. That's the one that sort of denies a whole heap of prefix ASs and then lets just specific ones in. Prefix list, ISPB out, so you're announcing your aggregate and maybe some sub-prefixes. Route map, I don't remember what the route map does, but it's on the next slide. Ditto for the ISPC connection. We've got a similar list of filters there. So rather than me making it up, let's actually look and see what I said. So ISPB, so I'm basically saying send the aggregate out, and then we've got this /21, which is say my dial-up customers, or broadband, or DSL, or wireless, or whatever. So they get to use this particular ISP path only. And okay, if the link to ISPB goes down, it fails over onto my main big pipe through ISPA. Okay, just by dint of me announcing the aggregate and accepting the default inbound. And this /22 could be for my expensive business customers. Okay, so I'm just leaking this /22 out. And so traffic to them will always use this path. So certainly inbound traffic will always use this path. Outbound, well, you probably have to do something to fix it to make sure outbound traffic for this address space goes out that link as well. Then the route map to ISPB, we do a single prepend on the aggregate and we leave everything else alone. And for the ISPC link, we do a double prepend on the aggregate. And so that means basically all traffic to the /19 will come in through ISPA, apart from traffic to the 21, which will come in through B, and apart from the traffic to the 22 here, which will come in through C. You may get some other traffic coming in through B and C as well, depending on the prepend you do here. So what can you tune in all this? You can tune the prepend, okay? You can tune the size of the address space you're leaking. And you can tune what's in the AS path filter I showed you a few slides ago as well. Yes? You certainly can. Snap away. You want me sort of waving hands or just standing still? Well, catch me when I'm waving hands. I can't wave both hands because I'm holding this microphone. But anyway. Okay. Right, so this is the type of thing. This is hugely configurable. So if you can master something like this, this is probably about all the BGP traffic engineering load balancing you'll ever need to do. So when I've inflicted this on a few people and, well, they seem to know what to tweak, they know what to change, because they're told, you can change this bit, change that bit, change that bit, change that bit. And going a few slides back, change this bit, change bits in here. And people seem to be quite happy to change bits. I haven't quite told them, don't touch this, it will break everything. I've told them, this is the configuration we're kind of going to work with. You can tweak the different bits here to get what you want to do. If you've got a quiet time of your network, see what happens if you miss out one of these lines. See what the volume of traffic is as a percentage of the overall volume. Because then you will know what impact overall it is on your inbound or outbound traffic. Okay? So it's pretty powerful trying to do all this kind of thing. Another thing is, it's actually very friendly for the routing table as well, because I'm not leaking tons of /24s. I'm just leaking the little bits that I actually need to leak. Right, so I converted in this ISP, I mean, was it a /19? I think it was a single /19. He was announcing 32 /24s. So I basically paired him back to 119, a 21, and a 22. So he's disappeared off the Jeff Houston Cider Report bad list, and he's way down at the bottom now with only got 2 aggregation possibilities. Okay? And they're very, very obviously traffic engineering ones, because you see the 21 and 22 with different AS paths from the 19 best path coming through the main provider. Okay? As I say, none of this is really particularly hard. What about outbound backup? Well, we can pop all this stuff into OSPF. I quite like using OSPF for convergence in the IGP, because it's a lot faster than trying to get IBGP to do it, especially when you're throwing around a reasonable number of prefixes. So originally the default on OSPF and router A, say metric 10, the backup metric 30. Set all the different static default routes, distances and so forth, and this all just falls out nicely in the wash. Just for lack of time, I'm not going to explain any of this because A, I'm losing my voice, B, I've got 5 minutes left, and well, it's pretty much self-explanatory, I hope. Anyway, the configuration will look something like, oh yeah, the IBGP I should mention. Notice the IBGP from router A, we're hearing the default route. I tend not to like passing default routes around by IBGP, because you never really know where they end up. It's probably better to pop it into your IGP, much faster convergence, and well, you don't want to end up with a private peering router carrying a default route. I've been burnt enough of that with that in the past that I really just avoid this going forwards. So this router, which is hearing the default, I've got a IBGP filter which basically says block the default, allow everything else. Okay, so let's move on to the last few slides. Communities. The first bit I want to look at is RFC 1998. Again, the guys at Internet MCI back all those years ago, I think it was 97 they did this, 96, 97, something around about then. It describes how to use communities for implementing load sharing, backup, and multiple inter-AS links. The idea here was to try and scale the configuration. Yeah, the counter says. To try and scale the configuration and simplifies the network operation on for the upstream. So again, scalability in mind. And what it defined was these 4 communities. So your AS number :100 meant if you heard that from your neighboring AS, you set local pref 100. If you heard your AS number :90 as a community, you set local pref 90, and so on for the other 2. Right? So if your neighbor sent you that community, you would basically change the local preference. I mentioned metric getting a bad name in the past. Well, this is what happened. Metric got a bad name, so ISPs used communities instead. So rather than sending a high metric, they would send a community upstream ISP AS number :90. That told the upstream ISP set local preference 90 on this prefix, and that had the same effect as using a high metric. All right. So that's really where this all came from. So the typical configuration on the customer router, you had a route map which basically handled all the community stuff, and the route map says anything we originate, we set community 100:90. So we set 100:90, our upstream is an AS 100. When they see that community coming in on our announcement, they would then set local preference. So we look on the upstream router. Here I've got various community lists here. Here's the one we're interested in. So for example, if the customer sent a prefix that had a community 100:70 set, he would set local preference 70. Same for set 100:80, set local pref 80, set 100:90, we set local preference 90. A lot of ISPs will use communities for signaling between autonomous systems. So if a transit provider supports a set of communities, you as the customer can then set a community on that prefix, and your transit provider would do what he said with that particular community. So it's really, really handy for trying to do fine detailed traffic engineering, load balancing, multi-homing, and so forth, that otherwise you'd have spent hours and hours with the upstream ISP's NOC just to try to make it work. So RFC 1998 is pretty straightforward. I'm saying here some ISPs actually support it. A lot more don't. Some people haven't even heard of communities yet. I find that quite amazing given they've been around for 11 years now. Some ISPs actually documented in the AS object in the Internet Routing Registry. Tends to happen more in Europe than anywhere else. They actually say what happens there. Some people put it on their website and say, we support the following BGP policies, send to these communities, we do this. Oh, speaking of that, here goes. I've got some examples. RFC 1998 is okay for simple multi-home customers, but of course, the real world is a lot more complex than it was back in 96, 97 now. So ISPs have dreamt up, come up with a really quite sophisticated set of communities that they want their customers to use. The idea really is to try and simplify their configuration and give their customers a lot more policy control than what they have. So that's RFC 1998 is an informational RFC. There's no sort of recommended standard for BGP communities, but we've got RFC 1998. We've got the 4 well-known communities. There was an effort a while ago to document what ISPs were using. There was the NANOG presentation at the last NANOG. Who did that? Richard Steenbergen, I think. Yeah, that's right. Richard and Tom Scholl did that, trying to document some of the common communities that folks were using. But again, it was, well, some ISPs are doing this, others are doing that, and so forth. These folks here, again, sorry, I've forgotten who actually has set up that site. But again, he's documented a load of different communities that ISPs actually support. So you can actually go to this one and find out which ISP supports what. So some examples. The first one I've got here, you probably cannot see that at the back. I'm sorry about this. Sprint link. So this first one here says 65,000:XXX. It basically means if you send 65,000: whatever, it will not advertise that prefix to AS whatever, where whatever is one of 166.8.209.29.14, 3300, 3356, 3549, 3561, 4635. Gosh, it's even smaller there. 701, 718, 702, and 8220, whoever they are. I know some of them, not all of them. Okay? So those are Sprint's peers. So if you send them communities with these AS numbers set, then they will do stuff. This one here, 65003:XXX, does a 3 times prepend. So if you send them 65,003:701, they'll do a 3 times prepend of your prefix towards AS701. And so on. More info at that URL. And that's the website there. It doesn't match, but that actually works. It just redirects you to this page. So they've got quite a detailed list of what they support. AAPT in Australia, some more examples. This is the former connect.com.au in Australia. They've got some support of communities there. I'm running out of time, but I've just got 3 slides left. So there's some more examples of communities they support. Verizon Business in Europe. So VisB, you can do local pref 80 with an AS702 if you send 702.80, 702.120. Various other ones, they've got 702:1 to do a single prepend, 702.2 to a double prepend, and so forth. You get the idea. More VisB ones. BT Ignite, I was talking about BT Ignite before. They're a very, very complex set. These actually work as well. I mean, I've worked with a few ISP who their customers had lots of fun playing around with some of these. If you send them 5400:1000, they will not announce your prefix to all their peers and transit providers. This really does work. If you send them 5400:2000, they'll do a single prepend, and so on through the list. Again, they've got all the transit providers here, and they've got some of their peers there, and a huge number more. You can look up the AS object to get the complete list there. Level 3, I've got a similar complex list. Last time I spoke to Stuart Bamford, it was like, not sure if anybody actually uses any of these, but anyway, they're there and they're done. I'd love to see the BGP configuration for this. It's an absolute massive list. But you get some idea of what's on offer there as well. So, suggestion, create your own community policy. I mean, I've got some suggestions up there. Have a look at the tutorial. Was it a tutorial? Was it a BOF? Whatever it was at the last NANOG. There's some more examples of what ISPs were doing there. If you don't use them for yourself, think about it for yourself. If your upstream ISP uses them, have a look and see what they support, because you might get some useful traffic engineering that you otherwise wouldn't get. Summary, multi-homing is not hard, really. It isn't. Keep it simple and stupid. It'll work fine. You don't really want the full table unless you kind of absolutely have to have it. Default route is just as good. If your customer wants 235,000 prefixes, charge them money. Finished. Thank you very much for that. Sorry for overrunning.